It is the problem of development in Russia of deterministic photon sources based on semiconductor quantum groups. Of course, now different problems are also pursued within this laboratory, but initially it was only this topic. This story started about 8 years ago in 2015, and I will speak now about the progress of this research done mainly in the framework of 4 bigger projects as listed here. First about the object of study, single photon sources. Actually, there are many types of single photon sources, and which one is needed depends on the problem to be solved. For example, if we like to make a quantum computer, in principle, it solves the problem. However, if you like to make a really scalable quantum computer with many qubits represented by photons, then single photons are not enough. And for this purpose, much more promising are states of multi-photon clusters. These are states where photons are entangled mutually between each other, for example, by polarization. And also, of course, if we are concerned with the system of quantum cryptography and quantum networks, you need in photon sources in spectral telecom bands, of course. This is also a problem. Initially, in my talk, I had ideas. I decided to stop mostly with this first topic, and it is mostly developed now, and in our group and in other groups as well. And also on this topic of photon sources for telephone bands, because the second topic we are working hard on that now, and many other groups are also working on that. It is absolutely impossible to speak about this in 20 minutes. Now I have more than 20 minutes. That's right, as far as I understand. So probably I'm speaking about this issue as well. But also shortly, of course. Okay. Single photon source. Actually, it is a very common thing. And any two-level quantum system, like atom, ion, molecules, semiconductor quantum dot, impurity, defect, whatever, it can need, and it will need single photons. If you excite this system, this two-level system, with laser pulses which are shorter than the lifetime of the excited state of the system. It's very simple, and the problem is not to obtain single photon emission, but to obtain very good single photon emission. And the parameters that should be obtained are listed here. First is brightness, that is probability to emit one photon per one pulse of excitation. It's very important parameters, and today, well, at least 10% is expected to be competitive. It is 10% obtained in a single mode optical fiber, not in the output of the device. Everybody is interested in what happens in the single mode optical fiber that can be used for that. Okay, then, of course, important parameter is single photon purity. That is probability of single photon, just single photon events. And it is, of course, characterized by the second order correlation function at zero delay, and it should be virtually zero, almost zero for in the modern devices really intended for practical applications. And for some applications, not for all, but for some applications, also indistinguishability of emitting photons are also very important. And they are characterized, indistinguishability is characterized as visibility of two-photon quantum interference, and for most applications it should be more than 90% at least. and for some application even more than 95 or 98%. So photons should be really indistinguishable. And it's not easy to fulfill these strict conditions simultaneously. And also there is also one very basic parameter. It's a wavelength of the emission, and of course telecom bands are very needed for many applications. For quantum computing, it's not mandatory, but it is also useful because there is an environment, and it's much easier to connect the processor with the environment if the photons are the same there and here and there. So it is also very useful. Okay. In fact, at least at present, there is only one system where at least most of these parameters, most of these conditions can be satisfied. And this system, it is shown here. It is one of possible design of this idea. It was first designed more than 20 years ago. This is pioneering paper about that. And the heart of this design is a semiconductor epitaxial quantum dot, grown epitaxially. Actually, in all modern devices, it is always indium arsenide quantum dot, and usually in a gallium arsenide matrix. And then this quantum dot is placed inside an optical microcavity, and this is very important because this is the only way to collect all photons in a single optical mode that can be then output in far field. And also it is very important to accelerate spontaneous radiative recombination due to the Purcell effect in microcavity. This is important if you like to obtain really indistinguishable photons, because indistinguishability of sequentially emitted photons is characterized by the ratio of 2 times. It is a coherence time of this two-level system and the radiative time of the emission. And of course, the simplest way is just to decrease this radiative lifetime by Purcell effect, because it is difficult to fight with the coherence time, much more difficult. And the quantum dots are usually grown, it is well known, by the Stransky-Krastanov self-organizing process, driven by lattice mismatch in the system between indium arsenide and gallium arsenide. And this technique, actually there are many disadvantages here, because first, it is very difficult to control the parameters. It is strongly non-equilibrium process, growth of such kind of quantum dots. It's difficult to control surface density. Then the location of these quantum dots is random. It's impossible to control it. Then size and wavelength of emission is also random. And moreover, it is spread in the wavelength range between 900 approximately and 1000 nanometers. And it's not a telecom band at all. It's a very different wavelength. So this is, everything is disadvantages. It looks like that. But only one thing is advantage. It is very perfect quality of this quantum emitter, and then possibility to monolithically integrate it with the semiconductor microcavity. And this is very important. It does everything. That's why this system is mostly pursued now. Of course, there are other possibilities, but for today it is best developed. And also, like different groups, we used molecular beam epitaxy to grow first initial planar heterostructures like this, where quantum dots are placed in a cavity. This is 1 lambda cavity between two multi-layer distributed Bragg reflectors, mirrors. And our contribution to this is that we can very thoroughly control doping profile in this structure. And it is very important because it is important to control the charge in the quantum dots. The quantum dots can be either neutral, or there can be one resident electron or hole, or two resident electrons or hole. And it is very important to know what we have there and to control this process. And this is what we can do now, and it's really very helpful. In fact, the post-microcavity with Bragg reflectors, it's not the only possibility. There are other possibilities of using different types of microcavities, like photonic crystal waveguide. Also, Chinese group represented bullseye cavity. It's also very interesting design, useful for many purposes. And in fact, you can buy these devices from French Candela or from Danish Sparrow Quantum, well, with quite perfect characteristics. So, but what is still needed? Okay, anyway, does not matter what is the microcavity, the heart of this device is always a epitaxial single quantum dot, indium arsenide, usually in gallium arsenide. And however, the problem is not only to produce a heterostructure with these quantum dots and to fabricate the microcavity. It is very important to fabricate microcavity exactly where the quantum dot is. So we should combine them, because obviously, in order this device operates perfectly, first the quantum dot should emit light at the wavelength of the resonance of the microcavity. The microcavity is high quality, and the resonance is very narrow. It is mandatory. Further, it should be placed, located exactly in the center of this lambda cavity. So how to do that? Different groups developed different techniques. Actually, there is no ideal technique to do that everywhere. Anyway, this process is not completely deterministic, because self-organization of quantum dots, it's not a deterministic process at all. It's not possible to control that, at least today. In our group, we used a very simple approach, but it is very effective. What we do, we first grow the structure, and then fabricate by photolithography it's array of many microcavities. There are hundreds and thousands of microcavity in a single, just one wafer, just one chip. Looks like this. And then we excite photoluminescence and look for the near field of these devices. Exactly in the cryogenic microscope. First we look just if some devices are dark or bright. Of course, if our quantum dot in some of these devices, if the wavelength of this quantum dot corresponds to the resonance of the microcavity, this is the only possibility to be bright. Otherwise, the light of quantum dots does not go outside. These small peaks are just these quantum dots which are not visible. So we first choose all bright dots, all bright posts, microcavities, and then look among them more thoroughly on the pattern of the transverse optical mode of this device. Actually, it looks like a vertically emitted laser. The design is very similar, functionality is very different. And then choose the devices where the pattern corresponds to the ground state, symmetric mode. And in most cases, it means that the emitting quantum dot here is placed exactly in the center of this post, exciting just this mode. And after that, we studied more carefully just a few devices, measuring photon correlations characteristics. And for that, a special setup, of course, was developed, allowing these measurements at cryogenic temperatures with picosecond time resolution, polarization resolution, many possibilities of correlation measurements, measuring statistics of different events, and finally found the device which is optimum, at least at that stage of the study. So what does it mean, optimum? Let me show. First of all, there are two possibilities. As I told, the quantum dot initially can be either charged or neutral, and it makes a great difference. because if the quantum dot is empty, no resident charges inside, then then after photoexcitation we excite a neutral exciton, electron and hole, with a Coulomb interaction, and the response emission of these excitons is not that obviously simple. It is a doublet with orthogonal linear polarization. And this is because in this strongly confined system, the electron-hole exchange interaction works strongly well, and it splits otherwise degenerate, 4 times degenerate excitonic states. Well, so we have doublet with orthogonal polarization. However, if the quantum dot was charged, then after photoexcitation we have a trion, a charged exciton, and in this case the spins of electrons compensate each other, and exchange interaction does not work. It's a quasi-singlet state, and as a result the emission is a singlet line with a circular polarization, of course, due to the selection rules on the angular momentum. Well, and it is the kinetics is absolutely different in these two cases. It is well seen if we use coherent resonance, strongly resonant coherent excitation by P pulse. And this is, no, pi pulse in English, sorry, yes. And this is probably the most effective way to obtain indistinguishable photons from this system. If we had trions, then it is a singlet, and excitation by pi pulse results in strongly monoexponential response. This is decay curve measured of a single quantum dot. It's a resonant fluorescence. But if we had exciton, then there is a splitting. It is a 3-level system, in fact, and there are always quantum bits there in the response. So time-resolved photoluminescence, resonant fluorescence, in fact, it looks like this in the case of exciton. However, in both cases, single photon emission is perfect, and I will show the parameters. The problem of this kind of excitation is that it is difficult to eliminate the laser light, because it's strong laser light exactly at the same wavelength. Of course, it's coherent resonant excitation. To do that, usually people use, and we used as well, cross-polarization filtering, and it means that 50% of the signal is lost, exactly. And it is very disadvantageous, of course. 50%, it's a lot of signal, yes, and it's disadvantageous. But anyway, this is quite an old spectrum of one quantum dot in a microcavity, probably the best one that we had previously, and maybe it is the best forever for us. I don't know, but anyway, it is an exciton. It was an empty quantum dot, and after emission it emits indeed 2 lines that are separated by about 3 microelectron volts. They are orthogonal. They had orthogonal polarization, linear polarization, vertical and horizontal. And if we measure time-resolved decay curve, it practically corresponds to the Fourier transform of this spectrum. So it means that this emitter is practically ideal. There is no inhomogeneous broadening, there is no spectral diffusion. The only decay channel is a radiative decay. That's all. So it's practically ideal, not 2 but 3-level system. In this quantum dot. At that time, it was maybe 2 years ago or something like that. There was possibility to compare the chip produced by this technique in Joffre Institute, and the bought photonic chip from Candela, French firm, that commercially sold it. Well, and one can see that both purity, G2 function at 0, and indistinguishability visibility of quantum interference is almost the same for both devices, and it is in fact quite perfect. Well, but the end-to-end efficiency in our device was essentially larger than in the French one at that time. Since that, there was great progress actually in Candela. Now they promise 30%, as far as I have seen last time in their prospects, 30% in single mode optical fiber. Well, and we expect to have this data maybe in the next year, 30%. But anyway, we are almost in parallel at this moment. We understand what to do further and go there. And using this device in the Quantum Technology Center, there was fabricated a system, developed and fabricated system of demultiplexing the sequentially emitted photons in 6 channel. And it was used, and it is used now in experiments on quantum computation. And well, Stanislav Straub, who is here, can much better answer and comment this point if needed about this demultiplexer and this device and its applications. Well, okay, but anyway, in the heart of that, it is just that chip that I showed you how it was produced. Well, so it is clear now that such parameters as indistinguishability and purity are in state-of-the-art devices practically ideal, almost ideal. It is possible to produce very good values, and the problem is to obtain the needed end-to-end brightness. It is still not large enough for many, many applications. So how it can be done? One very elegant idea, it was suggested by Chinese group 4 years ago or something like that. The idea is to produce the microcavity not exactly cylindrical, but with an asymmetric dichroic design. Well, for example, elliptical design. And then the ground optical mode of this system, otherwise it is degenerate in its cylindric system, it is splitted into 2 orthogonally polarized modes. And then it is possible to excite quantum dot in one polarization and measure in different. And this is a very fruitful idea to avoid losses during the cross-polarization filtering. Just well, it's a symmetric situation, so we can increase the detection at certain wavelength, but the emission of the laser line scattering is not okay. Thank you. Okay, so we are also working on that, producing now elliptical cross-section structures like this, and really it is a very fruitful approach. There are many problems, of course, here as well, but it really works, yes, and we hope that 30% next year will be quite available. And this is the best device. Let me show you the best device ever produced. It was, well, all approaches are concentrated here that were known, and additionally, it is very important, it was an open cavity. It was not completely monolithic. The top mirror was fixed on a piezo alignments, piezo drivers, so it was possible to adjust optical mode to the found optimal selected quantum dot. And also such microcavity could have very small losses, and as a result, a fantastically high 57% end-to-end brightness was demonstrated. Well, the problem is that this system is very difficult to operate. It's vibrationally unstable. So you can imagine what should be the accuracy of and stability of controlling the position of this top mirror in piezo elements. It's a real problem. They say, well, but anyway it works, and this is certainly perfect. And then in the rest minutes, I will briefly speak about the prospects of obtaining photon sources for telecom burns. Our first experience concerned O band. It is 1.3 micrometer. And how it is possible to increase the wavelength? First, nobody wanted to change the material of the quantum dot. Indium arsenide is a perfect material for that. So the only possibility is to change the barriers, the material of the barrier, and also the substrate. It means to change the elastic strain in the quantum dots, and that is also important. So we chose this system first, and it worked. However, there were many problems. It is difficult to control surface density of usual quantum dots in gallium arsenide, but in this system it is much more difficult. Also, this material is lattice mismatched with gallium arsenide, so it's difficult to produce Bragg reflectors, multi-layer system. To show single photon emission, we used different approach. We used photonic nanoantennas, this kind of cylindrical, very thin structures with a varied cross-section diameter. Well, and finally obtained the single photon source working in the telecom spectral band. Well, okay, however, the parameters you can see are much worse than the parameters obtained for conventional structures emitting at about 920 nanometers, much worse. And as far as we know, nobody else in the world produced this kind of structures with much better parameters. It's a common problem. Well, even more people are working now on photon sources for the C-band, 1.55. And this is the most common spectral telecom band for the optical communication lines today. These are just very many papers actually, and these are just this year 2 papers from 2 different teams, 2 different approaches. First approach, the same indium arsenide quantum dots, but grown on indium phosphide substrate in indium phosphide material, material for barrier layers. As a result, lower strain in quantum dots, larger size of quantum dots, and again smaller band gap of the barriers. It worked. And another approach demonstrated was, in general it's similar, but using gallium arsenide substrate and metamorphic buffer layer that accommodated strain between the substrate and the active region of this device. And in both cases, circular Bragg grating cavity, like bullseye, I showed it previously, was designed, and it worked. G2 function is perfect at 0. However, the end-to-end efficiency is 6.3, and that is the best value obtained for today. Well, it is 10 times worse than in the conventional indium arsenide, gallium arsenide quantum dot. And we use even third approach now. We grow the structures with indium arsenide quantum dots, also on indium phosphide substrates. But as a barrier material, we used for ternary and ternary solid alloys, lattice match to indium phosphide. And for today, we reliably obtain single quantum dot emission. It works in the O band, well, correlation measurements are currently in progress, and we believe it's the matter of very short time now. So to summarize, sources of single indistinguishable photons for this wavelength. It's a matter of engineering problem, not a scientific, probably, almost at least. Maybe some principal ideas appear, but today it is yet engineering problems. But sources of polarization and entangled photons, and I had not speak about that, not much time for that. And photon sources for telecom burns, this is just on the stage of proof of concept experiments. But everybody works on that, and it will work for sure soon. Well, and these are my colleagues. Actually, more than 30 persons are working on that now, on this research. Well, and these are just maybe key points, key persons, so I acknowledge their contributions. Well, thank you for your attention.
The meeting is open for questions and comments, please. Excuse me, very interesting, but can you clarify for me? There are single photon sources in diamond. They emit in the visible, so is it definitely the disadvantage? And also, what is the question about cooling with semiconductor devices? Do you need cooling or not?
Okay. First device, we just discussed it briefly with Igor Vlasov. Yes, well, there are applications for visible light as well. And one application is atmospheric connection lights, because this is just the region of transparency in the atmosphere. So maybe there are other
Satellites.
Well, one more very important applications, impurity. I'm not sure about impurities in diamonds, but impurities might be very important for design of quantum repeaters, quantum memory, quantum repeaters, and that is not working in quantum worlds. So it's also advantage of this system, at least in general. Well, as for temperature, this is a definite disadvantage of semiconductor quantum worlds, only low temperatures. So we are working at 10 Kelvin here mostly.
Because you never mentioned it.
I talked about cryogenic temperatures, of course.
Only for detection.
For detection too, but for cooling system as well. Certainly. Yes. But, well, that is typical. That is everybody, for a long time, everybody, how to say, смирились с этим. Nothing to do with it. Yes. So for me, it's nothing to do.
Yeah. Thank you. Other questions? I have a question. When you're talking about the design of the cavity, you are talking about the cavity layer with the optical thickness of lambda. However, I can imagine another types of the microcavity, for example, with half wavelengths. Could you comment, is it really important to have lambda thick microcavity spacer?
No, maybe it's not that important because indeed you can use a half lambda and 2 lambda and it will work. It depends on the goal and on the design. For example, if your design with dot layers, PIN structure, then it is sometimes useful to increase the cavity length because you can then avoid doping in the center where you understand this. So it depends, but of course it is possible.
Thank you. Other questions?
I'd like to ask you, the Quantella is now the leader in this field. It's my opinion because they have the real technical applications, really. And if I understand you right, your results are very close to Quantella, or it is some problem with this because it is very complicated technology.
I told you about the results and showed data over maybe 2 years old data actually, because at that time it was possible to compare two devices in the same condition, in the same setup. It is very important because you can write everything in the internet, but when you put this structure in the real setup, you obtain different, absolutely. Unfortunately, now we cannot compare because we are под санкциями, and Quantella does not sell us there. Yes, but if to look in internet, yes, they have progress indeed. We also have progress, but well, and I agree completely with you that they are very, very good scientists and doing very good business and science. That's for sure.
Thank you. Other questions or comments? Okay, in this case, let's thank speaker again. Our session is finished, so you're welcome for the coffee break.
Не обманите, это вы работаете с не буду нормально.
А23, 121. Да, конечно.
Система должна очень сильно чем нас. Нам сложно все это совмещать. Мы как бы не обязаны это делать. Нам делаться некуда. Потому что возможно качество точки пока есть одна техника, которая позволяет я совершенно не отрицаю этой техники, не удалось, но если вы еще растят, наверное, так я не девушек по обычке, как-то позицию дорогу, пожалуйста, найти. Но качество перед там риска. То есть если вы рассматриваете качество с точки зрения, там, я не знаю, излучающих,
там ДНКшки, ПКшки. Вот. А у него это на условии, конечно, не видно. Там, короче, уже полез закупили. ICTF, по-моему, какой-то не свой, этот, не очень последняя модификация, вспоминается, последняя себе операционка. Там EXFAT, есть он делает, есть просто FAT, нужно просто фатик. EXFAT это более-менее какая-то максика, она так и кривая, но сложно надо прям FAT закидывать. И то FAT не все считает, как-то это флешка зависит от этих красивых чипов.
Ну вот такое это было.
У меня просто, знаешь,
уже.
у меня вот наушников на записи купил, две флешки одинаковые. Я на маке делаю FAT, прям FAT форматирую, чтобы можно было закинуть на CD проигрыватель. Одну флешку читается, проигрыватель, другую нет. Просто как бы флешки одинаковые, а видно чипы какие-то разные, запаяны, поэтому они не все читаются. Ты нагадаешь. Так, ну все нормально, да?
Да все пока да.
После вчерашнего, да.
Раз, два, три, раз, два, три.
Нет, просто проблема в том, что проще зависит от того, что вы хотите, а не различимость не получить. Ничего страшного. Чтобы получить различимость, нужно резонансное наблюдение. Ну, непонятно. Мы тоже думали над этим, было бы здорово, конечно.
Привет, Саша.
Говорят, что я буду, да. Так что полверды, да.
Все, я готов.
3 минуты. Пойдемте.
Вот это, да? А вы видите тогда. Что надо сделать? Сейчас. Все, включено. Все, я готов.
Good afternoon. We should start next session. And I'm expected to be a chair of this session. It's spontaneous for me. And the first talk will be given by Andrei Fedyanin. Welcome.
Thank you, Mr. Chairman. Let me thank the organizers who kindly invited me to this conference and give opportunity to deliver the talk. I'll be talking about the experimental works what we've done in our laboratory in the Faculty of Physics and devoted to the use of surface electromagnetic waves, of special kind of surface waves called Bloch surface waves for elements of integrated nanophotonics. Actually, in photonics, there are plenty of work dealing with the surface electromagnetic waves, but majority of them are focused on the surface plasmon polaritons. And actually, plasmonics is the field of optics which deals with the prospective applications of different types of surface plasmons for telecommunications, for sensing, and something like this. However, there is a main bottleneck of plasmonics related to the ohmic losses, just because of the presence of free electron plasma in metallic systems. Therefore, we are trying to switch the paradigm of surface plasmon polaritons to another types of surface waves, so-called Bloch surface waves, which can be excited in the dielectric nanostructures and therefore with high propagation length. If we consider the photonic crystal, then inside the photonic band gap, one can obtain a specific localized mode, which called Bloch surface waves, which cannot be excited from the vacuum because it's located below the light cone. And however, this surface wave is strongly localized at the surface of photonic crystals and can propagate for quite a long distance, for example, ranging from several microns till several millimeters. And actually, the only source of the absorbance of these surface waves is the scattering. However, the areas of applications of Bloch surface waves are not very well defined. There are several works related to the using of Bloch surface waves for sensing, for enhanced nonlinear optics, and for optical manipulations. Our idea is to use the block surface waves, which can be excited at the surface of one-dimensional photonic crystals, to fabricate the elements of integrated nanophotonics, which can be fabricated by very, very simple but very beautiful techniques of two-photon lithography, because by using these techniques one can fabricate the dielectric, polymeric waveguides or other elements of transparent integrated photonics. We came to this area more than 10 years ago when we tried to excite black surface waves and obtain the techniques of visualization of these black surface waves by using the dyes which are operated on the surface of photonic crystals. Later on, we studied giant goose hen effect, which is enhanced by excitation of the block surface waves and the surface of photonic crystals. And later on, we tried to obtain the light pressure and momentum transfer from the light of block surface waves to the tiny microparticle with the optically trapped near the surface of photonic crystal. Now we are switching from pure fundamental studies of physics of block surface waves to the using of these excitations for several elements of integrated photonics. And actually, we are trying to use them for splitters, interferometers fabricated by the two-photon lithography techniques. Let me remind you the optical effects of multi-mode interference when we have two waveguides. First, single mode waveguide, which is then conjugated with the multi-mode waveguide. And in this case, due to the coherent interference of the different modes in such multi-mode waveguide, at specific distance of this multi-mode waveguide, all the electromagnetic field is focusing in one point. On the half of this distance, the electromagnetic field is split on 2 points. And it means that if we cut this multi-mode waveguide at this specific length, we can split electromagnetic wave which is propagated from the single mode waveguide to 2 points. And we use this approach to fabricate the splitters of electromagnetic modes fabricated by two-photon lithography techniques. Idea is very simple. Let us print by two-photon lithography technique the diffraction grating to put the light from the free space to the integrated photonic circuit. Then we have the single mode waveguide, which then we print the multi-mode waveguide. And then, depending on the length of this multi-mode waveguide, we can obtain the splitting of electromagnetic field from the single point to 2 points, or to the single point and again to the 2 points. Depending on the length of this multi-mode waveguide, we can obtain the splitting of electromagnetic fields on the scales of several tens of microns. Experimental realization of such a structure is shown here. We were able to fabricate the integrated splitter, which consisted of the diffraction gradient to couple the light from the free space to these integrated optic elements. Then we have the multi-mode waveguide to split electromagnetic wave to 2 parts. And then again, 2 single-mode waveguides with two couplers to move the electromagnetic field to the free space. And then we detected the possibility to split electromagnetic light with the ratio 1:1. Then if we fabricate by two-photon lithography the phase shifter, then we can incorporate the phase delay in one of the shoulder of this interferometer and fabricate Mach-Zehnder interferometer, the atomic force microscopy image of which is shown here. And then we can obtain the elements which are related with the interference in such interferometer. If we are talking about the different schemes of excitation of the block surface waves, by analogy with the surface plasma, basically there is three main approaches. The one of them, which is the most frequently used, is so-called Kretschmann scheme, or prism coupling scheme, when we use the prism to generate the surface electromagnetic wave on the surface of metal, like in case of surface plasmas, or on the surface of photonic crystal, like in case of the Bloch surface waves. Another way is use the grating scheme, when we can couple the light from the free space to the surface of material. But actually, there is another, the third type of excitation, so-called Otto prism scheme, which is shown here, when we are using the prism, which is spaced on the small gap between the surface of metal on photonic crystal. However, to use the Otto scheme, one can use very small gap between the prism and the surface, and from experimental point of view, it's really quite difficult. However, by using the approach of two-photon lithography, one can just print a tiny polymeric prism on top on the photonic crystal in order to use the Otto configuration to excite Bloch surface waves. And actually, this is the scanning electron microscope image of series of prism which printed on the surface of photonic crystal, and they have two legs to be located on the top of the surface of photonic crystal, and some gap here, which is designed to be effective for excitation of surface electromagnetic waves. And in this case, just upon the normal incidence of electromagnetic field from this free space, the light can be directed to this space with the gap thickness of approximately several microns, and then the surface electromagnetic wave can be excited in the surface of photonic crystal. Actually, this is the experimental realization of such coupler, which is using the Otto prism scheme for excitation of Bloch surface wave with the sizes of this printed prism in order of several tens of microns. By using the different shape of this print, one can also not only excite the surface Bloch surface waves, but also focus them, and actually to control the propagation of surface electromagnetic waves over the long distance. However, this special size, the lengths of this prism is really quite large. It's actually upon approximately 15 microns. In nanophotonics, one can interested of using another small or tiny type of excitation of Bloch surface waves, and we propose another type of this coupler, which is called nanocoupler, and actually this is a tiny silicon microsphere, nanosphere, with the sizes of approximately 150 nanometers, which is located at the surface of photonic crystal. And in this case, just because of the presence of so-called Mi resonances in this silicon nanoparticle, one can obtain the excitation of the Bloch surface electromagnetic waves, which are excited by this tiny nano antenna, and then the Bloch surface waves can propagate along the surface of photonic crystals. Actually, this is the experimental realization of such nanocoupler, which recently published in Nanophotonics, when we are using the objective lens in order to control the angle of incidence of the electromagnetic field on this silicon nanoparticle, and then by small variation of wavelengths of excitation, we were able to demonstrate the generation of electromagnetic Bloch surface waves in forward or in backward direction. And actually, if we compare the efficiency of using such nanocoupler with the Kretschmann scheme, it's shown here. If we are speaking about the large beam diameters, like, for example, 10 micron size diameter, in this case, Kretschmann scheme is much better. However, if we are going to the approximately 1 micron size of a focusing beam, in this case, efficiency of such nanocouplers become much larger in comparison with the conventional Kretschmann scheme. One of the problems of the nanophotonics is fabrication of the active photonic elements with the sizes of basically in sub-wavelength range. And we propose the approach when we are using the perovskite nanoparticles, nanocrystals, which are located on the surface of photonic crystal, to make the combination of a nanolasing system which can excite this coherent electromagnetic radiation from perovskite nanolaser to the Bloch surface wave. And this slide demonstrates you how it can be obtained by using the small nanocrystal of perovskite, which was fabricated in ITMO Institute. Located on the surface of photonic crystals, we were able to generate electromagnetic laser, coherent laser radiation, which is coupled to the Bloch surface wave. Actually, this is example how it looks like. By using the backfocal plane spectroscopy, we were able to show that by excitation of the perovskite by external light, we were able to generate a green black surface wave, which is coherently propagated on the surface of photonic crystal. And by changing the parameters of these perovskite nanocrystals, we were able to change efficiency and propagation direction of this nanolasing radiation. The last example of using the Bloch surface waves for nonlinear optics is for ultra-fast switching of electromagnetic radiation. And for this scheme, we are using the Bloch surface waves which propagate on the surface of the photonic crystals, which is covered by the two-dimensional materials. And we experimentally use graphene, which is located, monolayer of graphene, which is located on the surface of photonic crystal, in order to switch locally the refraction, the real and imaginary part of the electric constant, just by excitation of surface electromagnetic waves exactly in the area of the graphene layer. In this case, we were able to switch by using pump probe technique, switch the reflection beam from the surface of the material which is covered by graphene layer with the characteristic time resolution of less than 1 picosecond. And actually the efficiency of such the nonlinear optical switcher appeared to be quite large. Finally, to conclude my talk, I've shown you several examples of integrated photonic circuits which can be used by utilizing the Bloch surface waves in order to probe or to demonstrate several characteristics of integrated photonic circuits. For example, we were able to fabricate the polymeric elements of Bloch surface space photonics and introduce them as a tool of fabricating the photonic circuits. Then we demonstrate the perovskite nanolasing, which can coherently excite the laser radiation in Bloch surface waves. Then we decrease the size of the elements which can excite Bloch surface waves to the sub-wavelength range by using the resonant silicon nanoparticles. And also Bloch surface waves can be used for realization of nonlinear optical switching. Let me finally thanks to the guys of our labs who did this job. Actually, all results I presented here were done by these guys, and I just present them. Thank you very much for your attention.
Thank you very much for the talk, and you are exactly in schedule. Excellent.
I tried, yeah.
Questions, please?
Thank you for the presentation. What's about polarization of surface waves? It's normal to lies in the plane, normal to plane of
Actually, it must be about surface levels. The polarization of surface level is fixed. However, in the case of Bloch surface waves, depending on the conditions, you can decide OS, OP, TE, or TL, polarized surface waves. So in the case of this, now semiconductor materials which are transparent in infrared or in diamonds, for example. Diamond nanoparticles also has large refractive index and they can be used for the investigation of new reasons. Okay, so time for a couple of questions.
Thank you very much for your talk, and very much excited with the beauty of your own geography. But I have a question for the last time. Which character exactly is which and by what?
We have the gradual scheme actually for the graphene. For the graphene, we are using gradual scheme. This one. So this is gradual scheme. So this is one-dimensional photonic crystal located on the top of the prism, and then you have a pump which excites the surface wave here. A pump which excites the block surface wave here. Then, since this block surface wave is specially localized near the surface region, they change the refractive index of graphene. And then, if we look for the reflection of the probe beam, this reflection can be changed as a function of time because of changing of the refractive index of graphene. But
actually, it is 20% like all this stuff.
Yeah, something like this. So we change the refractive index of graphene in order to change the reflectivity of the okay. Thank you.
Good morning. It is very pleasure for me to see many known faces in this room. And I started my presentation. But first of all, I'd like to say a couple of words. First of all, I am thanks to organized committee, of course, and personally, my friend Dr. Igor Vlasov, who invited me to be here. It is first. Second, it is a little bit strange for me that in this room I see only Russian speakers, but we use English. It is a little bit strange, but it is the rules of this conference. It is strange. Okay, but nevertheless, I will be used, of course, English as rules of this conference. So our work is spread between two organizations, between Lebedev Physical Institute, FIAM, and Moscow Digital Institute, Phystech. So it is two buildings you see. What shall we talk about? We will be talking about the photonic integrated circuits. What are they? Photonic wire bonds. What is this? Will 3D nanolithography help us? And the connections with quantum technology. I will be trying to give answer for these questions. And my presentation will be strange because it will be not formulas, it will be only some ideas and pictures. 2D printing always used the paper with the letters printed. It is 2D. 2D printing, and it is first of all was Bishen. Bishen, it was more than one, how much it will be? It is middle of the 10th century. And the next step was Johann Gutenberg. It was the middle of the 15th century. It was first printing book, Gutenberg. Next, how it is possible to get out of the plane? It is interesting because our world is three-dimensional. It is very interesting to have some subject that's similar, three-dimensional. And I'd like to say a couple minutes about this guy. It is very famous guy. He is on one line with the Shen and Gutenberg, because this is inventor, Hull, Charles Hull, Chuck Hull. Invention was in March 9. You see this data, and in the middle of night, he called it from his lab to call it to her, to his wife, and invited her immediately to be in his lab. She was very surprised because it was middle of night, but she arrived, and Chuck demonstrated her this similar, simple cup for coffee. And wife said, why you invite me only to see this cup? But Chuck said that it is historical moment. It is a cup for coffee, printed. It is not prepared other way. So it was the invention of three-dimensional printer. Couple words. He is now billionaire, of course. He has a lot of the patents, but it is a new era was started. So it is the range for 3D printing. You can see that this arrow. It is from micrometers up to meters, and you see that it is possible to print houses and print some small devices, so on. I will be talking about the, it is possible to, okay, let me see here. Optical lithography. It is some element of optical lithography. Of course, it is possible to use the two-dimensional optical lithography. It is now using very wide in different countries. Unfortunately, in our country, we have some problems with it. But it is important for production some chips. You know that it is key problem with this production of chips. And three-dimensional, it is much new and much more interest. For example, it's my opinion. And this again important that it is possible to product three-dimensional samples. Three-dimensional different objects. Two-photon photolithography. This technique gives us the very high spatial resolution, up to 10 nanometers. It is close to now to some electronic lithography. It is very important because it is much more cheaper. I will be trying to explain how it's work. It is possible to compare. First of all, this technique use the specific material photoresists, and it is photoresist is using it's possible to use by two ways. One way is using the effect of two-photon absorption and one-photon absorption. And in this case, you see that the value where you concentrate your laser, it is different. For two-photon excitation, the size of the spot where the laser concentrates is very small. It is very important. I will be now explaining. This is the method of the two-photon photopolymerization. A previous talk, Professor Fedyanin a little bit touched it. This is the femtosecond pulse laser. Then it is beam of this laser is focused on the substrate, and on the substrate you have the couple of photoresist. You see, is it possible to see? Yes, this is substrate, couple of photoresist. Then you concentrate the laser pulse inside of this couple, and then you can move. You can move substrate, or you can move laser beam. One mode is piezo mode, and other one is galva mode. It is two different, and as a result, you will have the very complicated 3D subject with very small size, because the main maybe here it is more clear. You can understand. This is photoresist. This is laser beam, and this is the how this laser moved inside of this in this drop of photoresist, and where the laser come to this photoresist, monomers transform to polymer. So now you have the polymer inside. So it is two setups which we used. One is homemade. It is much more complicated system, homemade direct laser writing instead. I have no time to explain more details. And this is the similar, but it is from Germany, nanoscribe, photonic professional setup. Now it is very important that now it is in Physical Technical Institute. We involved in some large project, and we tried to prepare the similar machine, but it will be a Russian nanoscribe. It is some results of it. This is a picture about this model, our device, which we constructed in frame of some large project with Ministry of Science and Higher Education. And two very important parts of this process. First of all is device, machine, and other one is photoresist. And previously, in many countries, using the specific photoresist, but in our case, we have the very close cooperation with this institute, Institute of Organic Metallic Chemistry in Nizhny Novgorod, and it is practically the same quality of these materials, because materials is very important, as you understand. And this is some simple results. And very important, I will finish this part, direct laser writing, because using this technique, you can practically write like you use pen. You can, but in three-dimensional. And you see that the position of direct laser writing technique is, this is speed, how fast is possible to write. This is resolution, and this is price. And price is much less than electronic lithography. So it is possible to compare. Photonic integrated circuits. I'm not sure that it is necessary in this auditorium talk more about it. It is a complicated system, and has some interesting applications. And it is photonic integrated circuits. You see that now it is very important generation 5 for this photonic integrated scheme. And you see that the main element of this generation 5 it is using the three-dimensional possibility. Advantages. I'm not sure that it is necessary you can only read it, because performance, it is clear, small capacitance is important, set up to, yes, okay, it is clear for this. It is the same in Russia. So photonic wire bonds, give us possibility, for example, to connect two different chips. You see this picture, chip 1 and chip 2. It is two chips. It is possible to construct three-dimensional connector. It is different elements of photonic integral circuits, and it is, of course, it is possible, it is necessary to have a small laser. For example, now we're working with VCSEL. VCSEL, it is perpendicular oriented laser. Then it is some part of some central part, and then you must bring the information to fiber. It is important. How it is possible to do? First of all, we must prepare some model of our waveguide, and then we can construct the photonic wire bonds, photonic decoupling. It is very important for photonic integral circuits, because if you need to send light in photonic chip in one direction and other direction. In this case, of course, it is in planar geometry, it is practically impossible. But here you see that we told Sobyaninskие развязки in Moscow. It is, we use it. And it is important. Then we tried to investigate how it is possible to integrate polymer connectors inside of the schema with real photonics. And you see that if you will be send the light from this terminal in one direction and sight in other direction, this is possible to have detector, and this is we have detector, and this we have some gap, and in this gap we can put this is our polymer insert. Polymer insert in this place. This is some measurements of the losses inside of this, and it depends on the shape of this insert. Microlenses. We have microscope, confocal microscope, and we see that using this confocal microscope for analysis, express analysis of this, because the size of this subject is very small, and practically it is possible to use this, by using electron microscope, RAM or other one. But now we demonstrate that it is possible to use the standard confocal microscope. It is enough to see our subjects.
5 minutes.
5 minutes? Okay, I will be very fast. Okay, thank you. For example, this is one example of the complex optical system. This is some results, and I will only show you our applications. It is possible to put this micro lens on the top of the fiber, and the single photon emitters. We tried to investigate two types: nanodiamonds with defect. It is we do partly together with Dr. Vlasov, and hexagonal boron nitride with vacancy. Of course, we have the standard Henbury-Brown twist interferometer. This is our setup where I can use, we can exploit not only the Henbury-Brown twist interferometer, but home system as well on this table. This is hexagonal boron nitride is this very attractive material, it's my opinion, for purposes, maybe we'll discuss it later. This is how it is work. It is different defect of the plate of hexagonal boron nitride. We need some cavity, and because we need to have the much more speed of this excitation inside of it. And in this case, you see that different materials, two-dimensional, and you see that only upline give us the possibility to use it under room temperature. It is all of this is unfortunately working in the critical temperature. It is large advance for this. Then we tried to use electrical anti-bunching to use our material between two graphene layer. And it is shortly I will demonstrate other possibility when we can produce some whole cup. And the cube and the cup, we put, now I demonstrate some plasmonic effect because we used the metal cube and surrounded by emitting quantum dots. It is procedure, how it is possible to do, and now it is very interesting for us. Next step, it is we tried to construct some resonator. It is name of this resonator is taburetka. It is a Russian word. It's very popular, and it is constructed, and you see that it is a picture after electron microscope, and we see that different legs of this, and it is covered by metal. And it is possible to invest if you will put inside. So first of all, it is necessary to find on the surface to find the emitter of light, and then it is possible to construct under this spot. You will be construct. Okay. So as a fiber optic lens, I told about it. This is how it is possible to put diamond in the concrete place on the we think about. The details, this is very important, only 30 minutes, 30 seconds. It is possible to make connections between macro and micro, because if you will be used, we can do this by our technique, 3D printing, and in this case, it is possible to construct some different details where you can put fiber, for example, here, because distance is approximately 100 microns, and it is possible to use the standard fiber for this purpose. So this is other example of different splitters. 2, 3, and so more. So it is possible, for example, to put here some sources of light, and you will see. Okay, it is practically all. Shortly used available to technical technique. Escape for planar geometry is possible for integrated PC. Extended give you very nice resolution. I have no time to talk more about. This is some results, and this is our team. It is my students, PhD students, and so on. It is we have lab, 3D lab in Fistech. Maybe it is all. Continue.
I'm sure there are many questions, but we are out of schedule, so please just short, please.
Thank you so much. This is really great technique. So
Yes, it is. Of course, it is possible because it is only depends of your fantasy. What do you like to prepare? We can discuss it and we can do it. It is not only this is examples. For example, we tried to prepare some lenses. We prepare some. I forgot name. For biology, it is very important. We can prepare some samples which we can put some biological material on these places. It is possible different applications in biology, in optics, in other fields. I'm not sure that it is okay. If you're interested, of course it's possible. Excuse me.
Maybe one short question.
Спросите по-русски. Я начал с того, что аудитория вся русскоязычная, и мы, тем не менее, мучаемся и говорим по-английски. Но это не мешает нам, так сказать. Да.
Я только за.
Очень интересный вопрос. Максимально разрешающий способность. И реально вообще вот сейчас реально это делать?
Конечно, реально. Приезжайте ко мне в Долгородный.
Скажите, какая?
Значит, смотрите. На самом деле, excuse me my Russian language, but it is, I saw on this floor the large poster, and in the end of this poster it is language is Russian/English, so it is correct. Мы можем использовать, я отвечаю, значит, за главным элементом вот этой самой 3D-печати, я об этом говорил, по-моему, ну, понятно, говорил Андрей Федян, значит, это воксель. Воксель это как бы three-dimensional трехмерный пиксель. Размер этого вокселя фактически определяет возможности планеты. Значит, там есть разные способы уменьшения этого вокселя, но стандартный воксель, необычный, это примерно 500 нанометров. Это такое как бы яйцо от вокселя. Яйцо высотой 500 нанометров в диаметре 100-120 нанометров. Стандартный элемент, на котором строится любая конструкция. Но есть разные методы, мы, в частности, это используем. Была диссертация моего аспиранта год назад. Это есть такое дополнение, называемый STEP, Stimulated Emission Deflection, в результате которого можно существенно уменьшить этот рост.
Еще вопрос. Размер поля, какой вы можете сделать?
Что?
Размер поля изображения.
Поле, вот это важный вопрос. Размер поля действительно здесь не очень большой. То есть у нас стандартно 300 на 300 микрон. Но можно сшивать. Но это уже очень сложно. И сейчас мы сейчас пытаемся в рамках этого проекта, который мы имеем с министерством, мы пытаемся сделать гораздо большую площадь.
А больше это сколько?
Ну, в принципе, это должно дойти до нескольких миллиметров, может быть, даже десятков миллиметров. Это возможно. Но это надо использовать так называемую гальвамоду. Это, в общем, там не очень все просто. Это отдельно. Хотите, поговорим отдельно. С удовольствием.
Окей, Коля, свежий голову, пожалуйста.
Good. Yep. Okay.
English.
Good. This is just a training for English, I would say. Thank you, Mr. Chairman, for your introduction. And of course, I would like to thank the conference organizers for giving me this possibility to present our work. In my presentation today, I will speak about the possibilities of changing the luminescent response of silicon-germanium materials in low-dimensional photonic structures. The work that I want to present was done by a team of researchers from the Institute for Physics of Microstructures Nizhny Novgorod, Skolkovo Institute of Science and Technology, ITMO University, St. Petersburg, and Rozhanov Institute of Semiconductor Physics, Novosibirsk. So, here is a brief outline of my talk. Today I will focus mainly on two types of photonic structures, namely on photonic crystals and low-dimensional disk resonators and their areas. If we look at the motivation of this work is related with the possibility to realize efficient radiating source for silicon photonics integrated circuits. If in 1985 the idea to realize silicon-based photonic integrated circuits proposed by Sorev and Lorenza seemed rather futuristic, at present silicon photonics is undergoing a boom in its development and opening up new areas for practical realizations. Nowadays, silicon photonics is associated with the prospects for the development of data centers and communication systems, quantum computers, laboratories on chip, neural networks, and etc. As the market review shows, the silicon photonics should increase by approximately 28% by 2028, but the main limiting factors here are related with the risk of thermal effect and complexity in the integration of on-chip laser function. So it means that the integrated photonic emission sources are indeed in great demand. So let's start with the results of our work. In our work, the structures with germanium nanoislands emitting in the wavelengths of between 1.2 and 1.8 nanometers were used as an active medium. Both the structures with germanium nanolayers located stochastically on the growth plane and the structures with the older germanium nanolayers were used in our photonic structures. The structures were grown epitaxially on the SOI substrates and contain between 4 and 10 layers of germanium nanoislands. Depending on the task, the waveguide layers in our structures varied between 220 and 630 nanometers. As I already said, we will discuss the two types of photonic structures, namely photonic crystals and disk resonators and their arrays, and some scanning electron microscopy images you can see here on this slide. The structures were studied by the standard microphotoluminescence method, and the methods of the microphotoluminescence measurements in so-called so-called radiation pattern geometry. In the latter case, the radiation pattern of photonic crystals was analyzed in relation to the gamma point of the brilliant zone and the symmetry axis of the reciprocal lattice of photonic crystals. And the measurements were carried out within a relatively small range of the wave vectors. And the special resolution of our setups was provided by the lenses with 10 and 50-fold magnifications. While studying the photoluminescence response of photonic crystals with germanium nanoislands, we first examined the role of the lattice period on the luminescence response. Here you can see the photoluminescence spectra obtained for photonic crystals with a hexagonal lattice of holes, and the lattice periods of photonic crystals varied between 525 and 1000 nanometers. Here you can see that photonic crystals are characterized by the intense photoluminescence response in comparison, in some cases exceeding the photoluminescence response of the initial sample by more than 2 orders of magnitude. Here is the spectrum of the initial unprocessed sample you can see here in the insert. The maximum increase in the photoluminescence intensity in this case was obtained for photonic crystals with the latest periods of 650 nanometers and 675 nanometers. And the increase in the photoluminescence intensity when compared with the initial unprocessed sample was 112 and 78 times respectively. So you can see also some specific behavior of the photoluminescence response. The photoluminescence spectra shift to the lower energies with the increase in latest periods. And the spectra shift through the emission range of germanium nanoislands, which is shown here by the dotted lines. Obviously, such behavior is correlated with the variation of the band structure of photonic crystals. And the results of the theoretical simulations carried out of band gap carried out for our photonic crystals is shown here. Here you can see that indeed the photonic modes of photonic crystals should move to the lower energies depending on the latest period. So his right figure shows you also some 3D representation of the theoretical results. And the simulation in this case were carried out in the relatively small range of the wave numbers in the vicinity of the gamma point of the Brillouin zone. And this figure shows us a series of the first order modes which should be observed in the experiment. And indeed, this series of modes was indeed observed experimentally. Detailed analysis show us that the maximum photoluminescence intensity which we have observed in our photonic crystals is due to the A2, to the single A2 and E2 modes for which the bound state in the continuum should be observed. This is evidenced by a break in the emissivity dispersion dependencies of these modes at the gamma point of the Brillouin zone. And actually, these bound states in the continuum states, they are characterized by the extremely high quality factors, and which is also evidenced in the experiment. The quality factor of our single mode of our single mode A2 was approximately 2,600. Another possibility of changing the luminescent properties of the active media in photonic crystals is associated with selecting the etching depth of photonic crystals. In this case, when the etching depth increases, the splitting and formation of photonic modes should be observed. And even with the large etching depths, it can be, we can observe the intersection and interaction of photonic modes. The results of the luminescence studies carried out for such photonic crystals are shown here. The results, the studies were performed for photonic crystals with different latest periods and varying etching depths. You can see here that with the increase in depth, the formation, you can see here the formation of photonic modes with the increase in depth of holes. And also, since in this case, we see the strong increase in the photoluminescence intensity. For this photonic crystal, the photoluminescence intensity is approximately 2,075 times higher than the luminescence response measured in the initial unprocessed sample. And again, the detailed analysis shows us that we have a deal with a mode which is characterized by the specific dispersion dependence. This is a flat mode, and as the consequence of that, this mode has a low group velocity. This is a true mode, the dispersion dependence of which undergoes changing because of the mode interaction. In this case, we have also a high quality factor for this doublet mode, and the quality factor is equal 1,400. We considered also we have considered also photonic crystals with a modified lattice in order, first of all, in order to obtain a so-called single mode regime in photonic crystals with the small angles of photonic crystal lattice. And the result of theoretical simulations of such photonic crystals you can see here. And indeed the experimental results show us that indeed we can obtain a single mode regime. However, because of the strong dispersion dependence, the spectrum line of the single mode is rather broadened, and the increase in the photoluminescence intensity is quite insignificant. It turns out that, in fact, we can observe also the manifestation of the photonic modes in the square lattices of disk resonators. The photoluminescence spectra of square lattices of disk resonators with different diameters are shown here on the right part of this slide. And the spectra are represented by the relatively sharp lines, the spectral position of which depends on the diameter of disks. In this case, we see also an increase in the photoluminescence intensity, and an increase amounts to about one order of magnitude. Actually, the theoretical results show us that indeed we can relate this mode, these sharp lines with some photonics, photonics modes of the photonic crystals. However, in this case, we have a deal with the higher order modes. If we consider a chain of disk resonators with the same diameter and the same period, it means with the same distance between resonators, we observe a collective mode. A collective mode is formed by the whispering gallery modes of single resonators, and this mode is represented by the sharp peaks in the photoluminescence spectra. It is interesting that the whispering gallery modes itself, they are not observed in the luminescence spectra of a single disk. And again, in this case, we see the increase in the photoluminescence intensity, and the photoluminescence intensity increases as the resonant wavelength increases by approximately 2 times. Let's move to the last result. Here you can here we managed to input a stack of the germanium quantum dots in a disk resonator, and the stack of dots is represented as contained the stack of dots contained only 4 germanium quantum dots, and we have observed the photoluminescence signal related with germanium quantum dots in this case, and the signal is maximum when the stack is located in the center of disk, and the intensity decreases when the stack moves towards the edge of the disk. And also in some resonators with large diameters, we can observe the interaction of our quantum dots with the whispering gallery modes of the disks. In this case, the stack of dots act as antenna and extract the radiation of whispering gallery mode in direction perpendicular to the plane of our disk. And finally, in the conclusion, I will allow only to say that the structures we are developing are of interest, considering the possibility to create on their basis active elements for silicon photonics and open up new opportunities for solving fundamental problems. So thank you for your attention.
Thank you.
Да, давайте.
Мне очень интересует, вы использовали в качестве генератора
Нет, мы еще не
это очень важная тема, и уже давно люди из этой локации продолбят. Когда вы, в конце концов, вы считаете, что когда делают генератор?
Хорошо. Приходите, попробуем. Yes, of course. If you say about the mean resonances, the quality factors is not really high. It's approximately is no more than 100. I would say.
Okay, but
okay. Any more questions? I have also a question. You told about silicon germanium structures, these wonderful results, but what about repeated with the different materials? I mean 3-5 like gallium arsenide or indium phosphide, is it possible?
Okay, right now, actually the story is following. We work with the structures we are developing. It means in our group we are developing the silicon germanium structures, using them as active materials, but there is a group which works with gallium nitride, and right now we started to realize such kind of photonic crystals on gallium nitride. And however, it also is very difficult. It depends on the technology.
Yes, so, of course it is.
It's not so easy.
Okay.
Good.
So, if no question more, so please.
Да.
Хороший вопрос, кстати, потому что это 20 минут, что это сейчас. По-моему, тоже, да, потому что я думаю, что мы не отдыхаем точно. We proceed to the next talk, and there is a change in the title of this talk. That's right?
Yeah.
So I just announced the new one.
Yes, sure.
Plasmonic microcavity as a platform for effective emission of color centers in nanodiamonds. That's this one, yeah?
Yeah, that's this one.
Okay.
Thank you very much. Thank you for introduction. Dear colleagues, dear ladies and gentlemen, my name is Romshin Alexey. I'm a junior researcher at Carbon Nanophotonics Laboratory, Prokhorov General Physics Institute in Moscow. The supervisor is Vlasov Igor Ivanovich. So today I will speak about the color centers in nanodiamonds, which are effectively coupled with noble plasmonic microcavity. So all of us know that for quantum technologies, for effective their development, we need the effective quantum node. So if you speak about the photonic technology, we need the effective single photon source to make some operations with them and to finally to get the key distribution, quantum key distribution. So, but before I will come to the results, I would like to share with you some sightseeings on Samara. So I really recommend subboarding on Volga. It's really impressive. And if you have time, you could visit the Goluboy Lake, which is located 100 kilometers from Samara. You could take the taxi, and the so here the deep of this lake around 28 meters, yeah, and in diameter it's around 10 meters, or only 10 meters. So yeah. And speaking about the scientific part, I will start from silicon vacancy color center in diamond. So its special structure is presented on the left-hand side. You see that interstitial silicon atom is embedded inside the crystal lattice of the diamond and effectively coupled with two vacancies, which are located on the nose of the diamond lattice. And this system forms the complex which could emit the photons at near infrared range, namely at 748 nanometers. It possesses the narrow zero phonon line, you see. It's its width around 6 nanometers, but it could be less, up to 2 or 3 nanometers itself, yes, without any cavity, so it's really quality color center. So, and it has the perspectives in applications in quantum technologies in atmospheric, I mean, as an atmospheric single photon source, yeah. So, and in our work, of course, single color center itself gives not enough photons, and we should improve the characteristics of the, I mean, emission characteristics. So, how could we do it? By, for example, by placing our nanodiamond inside plasmonic nanoantenna. So, this plasmonic nanoantenna was designed together with Alexey Grigorievich Vitukhnovsky laboratory in Physics Institute, the Lebedev Physics Institute. So, and this is the picture, schematically illustrates what is the structure. So, we use silicon substrate and spoil the film of the I mean, gold film, and after that, using nanolithography, we fabricate the nano holes inside this film, so call it nanopits, like small cylindrical pits. And the typical size of these pits is around lateral size, I mean, 500 nanometers, and that's an experimental result already. And here is the atomic force microscopy map, from which we are capable to estimate the height of this structure, or deep, it's better to say. So it's around 200 nanometers. And preliminary DTD simulations shows that we are working at resonance, at plasmonic resonance mode. So the structure will be used in experiments, in further experiments. So we, in this work, we developed by ourselves the pick and place technology, which allows us to transfer the specific nanodiamonds inside the nanopit or on the surface of the gold surface. Yeah. And for this, we need to apply a small droplet, water droplet, and use the microcapillary to catch the certain nanodiamond and transfer it by put the positive air pressure, I mean, through the another end of this capillary. Yeah? So the typical fluorescence map of nanodiamonds transferred from the synthesis substrate looks like this, and it is interesting that we could draw anything. You see here the famous relation H nu, and we here work with ND1, ND2, ND3 because they have the most efficient fluorescent characteristics. So these points was chosen to transfer them inside nanopit. But before we implement some measurements, we measure the saturation curves, time resolve measurements were also performed, and etc. And the same measurements were performed when the diamond's inside the nanopit. And this is how does the ND1 looks like inside the nanopit. So this is these outlines, orange outline the nanopit, and white one outlines the diamond particle. And it should be noted that at this stage, the diamond's nature are CVD, so they were obtained by CVD synthesis, and they contain ensembles of centers. So that's not a single photon. It's not a single photon source, but there are many of color centers. Okay. So here is an example of measurements for ND1. Here and after we will use the terminology that blue that's for nanodiamond in pit, and orange for nanodiamond on gold surface. You see here the typical spectra, fluorescence spectra for to these cases, yeah, and that inside the nanopit, diamond emits much more photons, and if we will compare the counts per second in saturation, the enhancement factor will be more than 60 times, so it's quite large enhancement factor. Yeah, and to analyze more properly the emission, we measured the first of all fluorescent decay rate and found that no changes. We observed no changes in lifetime of the fluorescence. So, and after that, we used the photoreflection microscopy to obtain the profile of the excitation beam waste. We used the 532 nanometers excitation, yeah. And look at that. Here, the orange for diamond on gold surface, and the blue diamond for diamond inside the nanopit, and they see that extinction of the excitation field is increased significantly compared to the diamond on gold surface. So probably it could contribute, or maybe be as a main mechanism of the pronounced enhancement. So we also performed the same measurements for ND2 and ND3 and found that the factors, enhancement factors, not so large, but still. And also the lifetime doesn't change significantly. Keep in mind, please. So to summarize the result, we made such a table, yeah, and here the this is the enhancement factor. It's a product of the collection efficiency, or in other words, geometrical factor of the fluorescence. Here is the quantum efficiency, and here is the excitation factor, how strong they excite our system. So this is the excitation rate, namely. Yeah, and by additional simulations, we estimate this factor is near zero, near unity, and this factor is near unity too, because we don't see significant difference between lifetimes for various ND. So, and by estimating this factor experimentally from the data from reflection microscopy, we estimate the factor 4 in D1 is only 4, but how do we explain the rest of 1? Because we see 60-fold enhancement, yeah? And we here proposed the hypothesis that since the saturation power decreases and lifetime doesn't change, the probable enhancement is related to the switch between different optical states of the silicon vacancy center. So it's in bright state typically when it's once charged, yes, but it has also two different dark states. Neutral silicon vacancy center and double charged silicon vacancy center. But diamond also contain many other defects inside the crystal lattice, and the most popular defect is nitrogen. So our hypothesis is based on when we put our diamond inside the nanopit, we by the processes which are quite similar with first resonant energy transfer, we effectively ionize the neutral nitrogen, yeah, and the negative charge is transferred to SiV 0 center, and it becomes SiV minus center. It goes to the bright state, and at the same time, SiV 2 minus could give the charge to the nitrogen to make it again neutral, yeah, and this one comes again to the CV minus bright state. So this could be the possible mechanism, but it of course requires more strict experimental explanation. Yeah, and of course we also tried the single CV centers in nanodiamonds. We used the same approach, but the diamonds were taken from different nature. They were synthesized by high pressure, high temperature method, and the typical size is around 30 or 40, 3 or 400 nanometers. So this is this SIM image of this nanodiamond inside the pit. And first of all, we proved the single photon nature of the color centered inside the diamond, yeah, and measured the saturation curve. After that, we measured the saturation curves, and surprisingly, we observed that no significant count per second in saturation changes, yeah? But the saturation power decreases 2 times, more than 2 times. So maybe this platform will open an opportunities to low power consumption platforms for quantum technologies, yes? So in conclusion, we thoroughly studied the optical properties of an ensemble CV centers in CVD nanodiamonds, which are placed inside the nanopit microstructure. So we demonstrated that the enhancement factor up to 62 could be achieved, yes, but the mechanism primarily connected with first enhanced extinction of the excitation field, and the second contribution is charge conversion of the silicon vacancy states. Yeah, and also we tried the single photon emission. We studied the single photon emission of CV centers and obtained that the saturation power decreases inside the nanopit, for diamond inside the nanopit. So this platform is one of the advantages of this platform is that it's really scalable and low consumable in power sense. Yes. So that's it. Thank you for attention. If you have questions, I would like to.
500 nanometers.
Yes.
So why 500?
Because we have.
Is it correlated somehow with dimensional size of nanocrystal?
Yes, of course it correlates, but okay, I will start from the point why 500. Because we did the preliminary FDTD simulations, we used the 100 nanometers in diameter diamond, yeah, and localized it at the center of this nanobit, yes, and observe, analyze the. We put also the dipole at the center of this diamond, yeah, and analyze the emission of this dipole and obtain that the effective enhancement occurs at this region, which corresponds to near 500 nanometers in diameter. Yeah.
And am I right? Is the height is also matter?
Yes, of course, because if you will have, if you have the big height, you will the field doesn't reach the emitter properly, so it also matters.
Questions? I have one. I wonder about the mechanism of enhancement. The enhancement is huge, and
yes,
it's a tricky question. Might it be that this is probably, at least there is some contribution from change in the far field angular diagram of the emission? Might it be in the plasmonic structure? I mean?
It's a good question, but we checked it theoretically. We did some calculations and obtained that we tried different polarizations of the dipole in the emitter, but we didn't get some reasonable results. So that's why we decided to put the CE collection efficiency near to unity. Yeah. But of course,
yes, probably it is.
Probably it is, but more in our opinion, that more contribution gives the. Okay, the geometric parameters are optimized for an excitation field. So the excitation is better than the emission directed to the objective.
I see.
Okay. Is it clear? Okay.
Okay. No question?
Thank you.
This is the our session.
Алло, вы меня слышите? Сейчас, дверь закрою. Да, у меня будет презентация. Нет. Есть, потому что сейчас, в режиме, Дарьи, то есть она показывает. Шишкина Дарья Александровна. М. Ну, камера есть, в принципе. Там как, не знаю, будет она показывать или нет. Нет, у меня, значит, внизу есть микрофон, потом есть, показать веб-камеру. Сейчас я её, по идее, включу. Не знаю. Так, вот. Но она, по-моему, не работает. То есть она горит, но ничего мне, во всяком случае, я себя не вижу. Вот, да, показать экран. Первый экран. Вы видите сейчас? Он загружает. Пишет, что, загрузка показа экрана. Так, остановлю. Так, вот, может быть, я здесь могу выбрать. Это слайд. Значит, если загрузить, то где его загрузить? Я вижу вот это, приветственное окошко Big Blue Button. Так, ну вот показ экрана. Раз, два, три, раз, два, три. О, все. Ну вот я пытаюсь, но она почему-то мне, то есть я вот когда включаю, я себя вижу. Потом, показываю, что включить камеру, но почему-то ничего не происходит. То есть камера у меня включена. То есть она вот загорается, камера. Сейчас я попробую, да. Так, вы меня сейчас слышите? Ну нет, а вот камера не включается, пишет, что ошибка сервера. Нет. Да, 10:20. Мгм. Ну да, так, попробуем сейчас, значит, вы ее видите большого размера или сейчас я попробую, значит, полный экран. Вот полный экран, то есть я тоже вижу ее нормально. И если я пролистываю, да, вроде бы даже это подгружается все нормально. А я вас тоже не вижу, кстати. М. Не, ну ладно, в общем, я вижу как бы свою презентацию, то есть я вижу только то, что я показываю сейчас. А, ага. Нет, так ничего не поменялось, потому что я вижу все время одинаково. То есть там вот, где вот это модератор, то есть как бы Шишкина Дарья, то есть я ничего не вижу, я просто вижу, что, иконку и все. Так, а если я вот сейчас я убрала презентацию. Вы ее не видите, да? Да, по идее. Да. Да, щас листается. А тут вот я, если, делаю убрать презентацию. Главное ничего не трогать. Я надеюсь, что у нас немного таких на удалёнке. Чтобы работает. Нет, не нет. Вот до этого слышала, то есть как бы было в самом начале подключения. Мгм. Мгм. Я вот пыталась до этого слушать видео, и очень, ну, то есть как бы плохо было слышно. То есть если что, тогда продублировать, либо, например, в чат вопрос. Ли понятно, да. Либо повторяйте вы, то есть как бы. Мгм. Вот, хорошо. То есть вроде бы жалко, конечно, видео не включается почему-то, потому что я камеру выбираю. Может быть, попробую низкое качество, если потому что я даже уже проверила в "Скайпе". В "Скайпе" работает камера, то есть нормально. Нет, у меня внешняя камера. Да, нет, написано: "Невозможно, достичь, соединиться с сервером. Медиа, ошибка 1020, 1020". И отключается. Ну ладно уж, как есть. Алло, ну все тогда, встре мгм, до встречи. Когда там так, у вас в 2:10. Да, у меня сейчас практически 11. То есть это в 12 где-то. Д 2 часа разница. То есть у вас сейчас 11, у вас сейчас час. Да-да, я здесь буду. То есть я так оставлю, я ничего не трогаю, чтобы уже работало. Всё тогда. Мгм, до связи. Спасибо за помощь.
Еще можно просьбу, иначе нас не будут слышать.
Хорошо. Okay, I will repeat it in English. So our time is limited because we wait the ship on ship. It will be very interesting, and I think that it is the main deal today. Okay, so now we start our session. My name is Alexey Vitukhnovsky, and I will be with you during the 1.5 hour. And first presentation will be done from Institute of Spectroscopy. Afanasyev, please. Who is? He is, and you are. You're here. Okay, excuse me. You have how much?
20 minutes.
20 minutes.
Hello, dear colleagues.
20 minutes, but you can use both. If you need, you can do some comments in Russian, because on the poster I told about, it is language, it is English and Russian, so you can combine.
Okay. There was a lot of interesting talks on solid state physics, and now my presentation will be about cold atoms, and our goal in Institute of Spectroscopy is to construct a quantum sensor based on cold atoms, and in the beginning of my talk I will give some introduction of quantum sensing and atom interferometry, and then I will describe the technology of atom chip and give some experimental results which we have in our laboratory now. Okay, if you want to construct quantum sensor based on cold atoms, we need atom source. Practically, it will be used. We can use thermal atomic beams, cold atoms, or BEC. And if we want to construct precision quantum sensor, we need to construct interferometer. The simple interferometer is we need to split our atomic ensemble on two ensembles. It is possible to do with pulse of laser radiation. We need half pi pulse. In this case, we can use Raman transition between the between the states which corresponds ground states of atoms, for example, rubidium or cesium. The next we need mirror. This will be a pi pulse, and when we need to recombine atomic ensembles with split again half pi pulse, and we have two outputs of such interferometer. This is a Mach-Sender interferometer, and the number of atoms in each of output will depend on phase difference, which determined this equation, and you can see that we can make a quantum sensor of rotation, this term, or acceleration, or gravity measurements if we work with this term of equation. And it is possible to use such sensors both for applied or fundamental physics. Mostly now it's used for fundamental applications. The first is investigation of Einstein equivalence, principle of equivalence, and there are a lot of works concerning on looking for dark energy, dark matter interaction, immersion of gravitational waves. In case of applications, it is possible to use such sensors as clocks on the board of satellites, or for navigation system, because if you have accelerometer, gyroscope, and clocks, you can construct inertial navigation system. And the main one of the main goal is to make a gravimeter and use it for exploration of minerals. I'd like to highlight two experiments. This is fundamental experiments. These experiments in space, and the first is the Project Myers. During this project, the first Bose-Einstein condensate in space was achieved, and the interferometry of Bose-Einstein condensate was demonstrated. And now on the board of International Space Station works called Atom Laboratory with the same ideas, and there are a lot of experiments on it. One of them is reaching the temperature till 40 picokelvins, and you can see the picture of Bose-Einstein condensation here, which creates on the board of International Space Station. And the main idea here is to use atom chips here and here as called atom sources. Okay, and now if we want to construct quantum sensor, we need efficient atom source. Not exactly cold atoms, but atom source. The first one is atomic beam. This is thermal atomic beam, and this is a very good atomic source because you can construct your quantum sensor which work in continuous regime, and this gives you high bandwidth of your for your experiment, but the dimensions of such quantum sensors will very high. And because of this, modern quantum sensors based on atomic fountain, like this one, it's utilize a three-dimensional magneto-optical trap with atoms cooled down till 10 or several microkelvins, and when trapping is switched off, atoms fall down, for example, in the gravitational potential, interacts with half pi, and again half pi pulses, making Mach Sender interferometer. And in this case, you can measure gravitational field, for example. But the problem is to increase the precision of such measurements, you need temperature less than 1 microkelvin. And due to you need some process of evaporation cooling. And in this case, you can reach Bose-Einstein condensate, for example. And this is very hard to do with such setup. The main problem is you need a high gradient of magnetic field. And such high gradient of magnetic fields you can reach with atom chip. In this case, you can make atomic ensemble with several hundreds of nanokelvins and use such ensemble for quantum sensing. And what is atom chip? We start from dielectric surface. On the surface, we need to form metal microwire with dimensions of about several microns. The width will depend on your problem, and you need to carry out a current through such a microwire, several amperes, and because of this current, you have magnetic field around the microwire, and if you have additional homogeneous magnetic field, in this case you will have some minimum of magnetic field near the surface of such chip, and this minimum of magnetic field can be used to trap cold atoms. The distance between cold atoms and the surface will be determined by these equations. There is some magnetic field gradient at this point, and you need to the currents about several amperes. And this is a problem because in case of ultra high vacuum of about 10 to the minus 10 power. This current is very high current. Okay, this is the scheme of our setup. Here we placed our atom chip, and we to cool down atoms near the surface of atom chip, we use additional 3D magneto-optical trap and a hole. We form atomic beam. Atoms cool down near the surface of atom chip. We can scan the point of atomic beam near the atom chip with additional 2D magneto-optical trap. And for example, in this case, using microwave generator and antenna, we can make some Ramsey spectroscopy to make atomic clocks. Here you can see, for example, atomic clocks based on atom chip from France. Okay, we have two types of wires on our atom chip. One wire, so-called U mode, the current flow is the letter U, and this corresponds to 3D magneto-optical trapping. In this case, we have quadrupole field distribution. This is some calculations of our chip in the U-mode configuration. And if you switch off green microwire, we will have current flow through the letter Z. And in this case, it corresponds to a three-dimensional analog of UFO-Pritchard potential, and it is used for magnetic trapping of atoms and reaching of Bose-Einstein condensate. The problem is if you have a current of about 3 amperes, the temperature of such a chip will very high, and in our case we can calculate this, and our construction gives us the possibility of working in continuous regime with magneto-optical trapping of atoms and the temperature less than 200 degrees. Here are some example of electron microscopy of our atom chip. Our atom chip consists of metal and grooves between the microwires made with lift-off lithography, and we need a full metal chip to organize reflection of laser beams from the surface of atom chip, because in case of atom chip we can't use an ordinary 6-beam technology of 3D magneto-optical cooling, and the laser systems the same as for ordinary cooling. Okay, and this is the photo of our setup. Here we place a 3D magneto-optical trap. The atomic beam goes through this direction, and here we placed our atom chip and cool down atoms near its surface and trap. And this is one of the first results. This is a cloud of rubidium atoms with a temperature of about 200 microkelvins, and the number of atoms is rather small. It's about 10 to the 5 power. The problem is can be solved with additional microwire. This is a wide microwire. In this case, this is our new generation of our atom chip. It works but with temperatures less than 100 degrees. And if you compare the magnetic field distribution from thin microwires and wide microwires, we can see that in this case the magnetic field is not clear along the black lines. Black lines correspond to the ideal quadrupole field gradients, and you can see that here, for example, and here the vector of magnetic field perpendicular to this line. In case of white microwires, this gives us more proper direction of magnetic field, and because of this we have the volume of trapping much higher, and you can see that if we use narrow wire U mode, we have atoms less than in case of U wire magnetic U wire mode. And to demonstrate the efficiency of our atomic source, we can investigate the loading curves of atoms to magneto-optical trap here. We can do it with two possible ways. We can switch on so-called dispenser near the atom chip. In this case, the pressure, residual pressure will high, and because of this, the lifetime of atoms in the magneto-optical trapping is low, and the number of atoms will very low. And if we use loading from additional atomic beam, you can see that the number of atoms increased, and if we use additional 2D mode to scan atomic beam near the surface of atom chip to have a good results, we can increase the number of atoms, and the lifetime in this case is very high. And with such atomic ensemble, we can make some spectroscopy. The first is we can optically pump atoms on the hyperstructure sublevels of rubidium atoms and switch off atom chip and switch on the microwave generator. And changing the microwave pulse duration in accordance with quantum mechanics, we can investigate the number of atoms in the excited state. In this case, we can see the Rabi oscillations between ground state and excited state, and increasing the power of microwave generation will increase the frequency of Rabi oscillations. This is the black curve. Okay, and
please note 3 minutes. 3.
Okay, it's the end. And now we can make some spectroscopy. We can tune the frequency of microwave resonator through resonance, and in this case we have Rabi spectra. This resonance between F equals 0, F equals 0 magnetic sublevels, and you can see that there is shift of spectrum. It corresponds the second order Zeeman shift because we have some additional magnetic field here. And if we will use two pulses, half pi pulse and half pi pulse, we can, in this case, we will have Ramsey spectrum, and the fringe, the width of the fringe will depend on interrogation time, and in our case, it's about 1 kilohertz. And at the end, some example of magnetic trapping near the atom chip. We have the cold atom ensemble near the atom chip in the white U mode. When we switch off white microwire and we have thin U mode near the surface, in this case atoms goes to atom chips and compressed. You can see it in increasing of luminescence here, where concentration of atoms increased. And afterward, we switch off the green line and catch atoms in the magnetic trapping. Okay, at the end, in our laboratory, we use atom chip. This is the first atom chip in Russian Federation, and now we can make some spectroscopy with atoms called cooling near the atom chip. And as the next stage, we will use spectroscopy of atoms trapped in magnetic trap. Okay, thank you for your attention.
Okay, thank you. Now we have short time, maybe 2 questions, not more. Who can ask something? No? In this case, I will ask, why you use rubidium ions? Is it now the best material in this business?
Rubidium is maybe one of the best alkali atoms for this aim, because you have commercial laser diodes in the line of rubidium, and rubidium is the second standard of frequency, and the frequency, the spectrum which I showed, this corresponds to clock transition in rubidium, and this is a second standard.
Okay. Can somebody ask? Oh, please.
Can you say anything about beam quality laser beam,
No.
which you applied for probing?
Beam quality? Gaussian beam from fiber. No, magneto-optical trapping. For magneto-optical trapping, you need a wide beam about 15 millimeters, and there is no specific problems with this if you want to have an atoms. Of course, you need the more problem is the balance between the beams. For example, here you have intensity in this direction and in this direction. The most problem is this is balance between intensities, but not the quality of beams.
Okay, excuse me, but we have no time for next questions. But I recommend to use the desk on the ship for discussion. Палубу. Предлагаю использовать палубу корабля. Так. Кто у нас следующий? Who is next? You? Вы, да? Окей.
С кого вы еще раз?
Как вас зовут? Просто как вас представить?
Окей, хорошо.
Как? Алексей Калмыков. Okay, so it is next speaker, Alexey Kalmykov. He will be do next presentation instead of Dr. Melentsev. It is again Institute of Spectroscopy. 20 minutes.
Okay, thank you for introduction. My name is Alexey Kalmykov, and the topic of my talk is quantum nanoplasmonic for biosensing and bioimaging of the level of single molecules and variants. Initially, the name of Pavel Melentsev was mentioned in program as a speaker, but unfortunately he couldn't come here. So, as a course, I will be a speaker today. So, our team who performed measurement is from Institute of Spectroscopy. The samples and procedure of sample preparations connected with biology was made by Denis Kudryavtsev from Shemyakin-Ovchinnikov Institute of Bioorganic Chemistry. Some samples plasmonic nanoparticles with Koshel plasmonic nanoparticles with diamolecules was made by Boris Hleptsov from Saratov University. And some analysis of some electron microscopy analysis was made by Roman Kirtaev. So this is our team. What is the topic? The topic is modern purpose of nanoplasmonic is to localize energy, and some practical application in finding some viruses or biological object in a very low concentration is to find single molecule. Not low, but we need to count some viruses or some molecules. So it's important. To understand the scale of this problem, we must consider the size of wavelength. It's about 1 micron. But some practical important concentrations are such that the distance between molecules this distance is about 40 or 30 microns. So it corresponds to typical concentration about 10 to 7 or 10 to 8 power particles per milliliter. So we can imagine that these sizes are very different. So and if we go to the volume task, for example, to put this distance in the third power, we will understand that it's very difficult to find one molecule in the volume of the liquid. So I will show 2 examples how we find how we solve this problem in our lab. The first example is control and determination of troponin molecules in blood. It's very important task to prevent and to work with cardiac diseases. So troponin molecules are is indicator of illnesses connected with heart. Under supply, with lack of oxygen, our heart muscles start to destruct. So in blood, these troponin molecules get with the process of heart muscle destruction. So when people are healthy, the level of troponin molecule is very low and we can't detect it. And with development of the illness, it increases very sharp, and we must find the moment where we can help this person when it isn't late. So this is the first task, and practically important level of concentration is about 10 to 7, 10 to 8 power. It corresponds for 1 or 2 picograms per milliliter or such distance. The second example we study in our lab is detection of coronavirus particles. In the liquids of ill human, the distance between 2 viral particles is quite large for detection. It's about 1 millimeter, so we use amplification, polymerase chain amplification of viruses to find the to provide the analysis, but it's very difficult to count viruses in the sample without amplification. So it's also a very difficult task. And both of these tasks are connected because both of these molecules are not fluorescent. So it's very difficult to excite them. So you need to mark them with antibody labeled with different fluorescent marks. So we use some antibody synthesis in Institute of Bioorganic Chemistry to label troponin molecules, and the same with coronavirus particles. It's very important to connect as much as we can labels in order to increase the signal to noise ratio and to reach the best level of detection. So how we can find these molecules? How we can find the concentration? When concentration is so low, about 1 or 2 molecules in the volume of registration, we need to count this signal. And the time when we can analyze all the sample, all the volume of sample, is very long, because molecule get into sharp laser beam focus very rarely. So we need to wait for a long time to get very low errors in our measurements. So typical approach with hard focusing beam isn't very suitable for this purpose, to detect so low concentrations. In order, the reason we need to mark our sample, localized, non-localized sources of light is very important. There are several different objects in this topic. We work with diamolecules usually in our lab, but these problems are connected with diamolecules because the spectral, typical spectral width is very high, and diamolecules have such a property called photodegradation, and the signal of this object unstable, signals unstable, and we use nanoplasmonics to fix all these problems. I mean, nanoplasmonics help us to control photodegradation, control the photon flux from our samples. So this is the decision how we can improve our marks. So plasmonics is part of quantum technology, because plasmonics can have all properties which are suitable for the photons. I will mention all of them, but for us, only some of them are important today. It's a weak and strong coupling, quantum size effect, and nanolasers. It's also a good mark for different biological objects. So how we can compare photonic mode, photonic cavity, and plasmonic, nanoplasmonic resonator? The main difference is the size. Size is one order difference, but for the mode volume, we have 3 orders of magnitude difference. So this reason why plasmonic cavity help us to get such quantum emitter and mode interaction, which is very hard to obtain in photonic. Very small, tiny cavity volume is very important for weak and strong coupling of emitter to cavity. Weak coupling is quite good studied with weak coupling with plasmonic devices, and one of the best scheme where it is realized is published in this paper by Vladimir Shalaev, and they obtained the best result in this field. Maybe they have 3 order shorten of lifetime of excited state, and the photon flux from such scheme was increased compared to the free space nanodiamond. So we also try to work in such scheme, I mean quantum emitter and plasmonic nanoresonator, but with another objects. We work with metal quantum dots, it may be called so, or silver clusters. It's system or consists of several atoms of silver. The number of these atoms is about 10 or several tens. So the number of atoms in our cluster determines the energy levels and the position of the spectral fluorescence. So we work with a system about 17-20 atoms of silver. But these results are well known in literature. A lot of people work, not a lot, there are only several works about cluster, but they are studied quite well. But the initial spectral width of such quantum emitters is about 30 nanometers, and it is a typical lifetime of excited states. This result are for clusters which the average number of atoms is 17. But we want to put this quantum emitter in a plasmonic cavity, plasmonic resonator. We find such system where this task is realized automatically. I mean, some argentum nanoparticles, it's percolated silver film, and between big nanoparticles, size of which are about 50 nanometers, we can see different spots. This is a transmission electron microscopy image, and this is the magnification of this one. We can see small particles. In red, we can see the number of atoms. We published this result in previous year, and in the article you can find, for example, some electron diffraction of this sample, and it's shown that its atomic clusters consist of silver atoms. But compared to the previous results connected with free electron clusters, we work in resonator. So we find not wide 30 nanometers spectral peak. We find in our system narrow line. Its approximate width is about 4 nanometers. This is a result. This result is very important because the use of plasmonic nanoresonator help us to narrow the line width and to shorten the lifetime of the excited states. So the photon flux from such system was very high and allow us to detect the signal by the naked eye, of course with use of microscope, but we can see it without any CCD, only with our eyes.
Excuse me, I need to say only 1 or 2 minutes maximum.
I have lack of time.
You have, because time is very short.
Oh, so I'll skip a part of result. The second important result is strong coupling. Its process when interact the plasmonic resonator with quantum emitters. Here we have the next result. We stabilize the photodegradation process, which is connected in oxidation of interplate states of molecule. In order we have a hybrid state which have two levels, split levels, in order to interaction of dimolecules and the resonator. And this help us to lower the population of triplet state and dramatically decrease the photodegradation process. We have find that this process is resonance and depends on concentration of the molecules, but this is the introduction to another part of our work, how we use these objects to detect some biological or viral particles. This is, I think, the most interesting part. So it's quite all. The result I will skip. It's a detection of troponin molecules labeled with cyanine dimolecules, and we reached here some unique result. Our results are better than all commercially known ways how to detect troponin molecules with very low level of the detection. So it's very important, but our next results, which are now under publishing in Nano Letters magazine.
Excuse me, I suggest to maybe skip
okay, I'll skip
SARS because now SARS is not so dangerous for us. Maybe it is better to go to conclusions and say that's the main idea of your talk.
Okay, I'll say only that labeling of coronavirus help not only to find coronavirus particle in the analysis, it help only to also to distinguish a viral particle and pseudo-viral particle with different number of the spikes, because this number of spikes determine the level of the signal, and low level of signal can say that here isn't a viral particle, a pseudo-viral. For example, there are two real viral particle, but this is another part. And we prove this measurement with electronic microscopy and show that this really is this object, this viral particle, and the particles with low signal is the particles without any spikes, so-called pseudoviral particle. So some outline. First, the topic is quantum engineering, how we can change the properties of emitters with strong coupling, with weak coupling, and we reach some results in this topic. Second is designing of the hybrid nanoparticle, plasmonic nanoparticle with shell doped with dimolecule. We can change these properties and show the use of this object to detect some biomolecules and variants in important samples and important tasks for society. And this is our team from Institute of Spectroscopy, some people who connect with theoretical estimation and calculation, and people who help us to fabricate and characterize our samples.
Okay.
So thank you for your attention.
Okay, we have only time only for one question, but the main key question, who will ask?
The person is behind you.
Ah, okay. Michael.
Thank you for your presentation. I have a question about stability of your hybrid structure.
Yeah.
Is stable?
Okay.
For how long?
If I answer in short form, yes, it's stable. We have reached about 1 order. We increase our stability more than for 1 order. So here I present the graph, but it's very. I skip this part of talk, I think. So here we can see the typical graph which corresponds to photodegradation, and the blue graph is our optimum nanoparticle, but here is free, so you can see the difference.
Okay, so excuse me, but we must move because the captain of boat will not wait us. So next is Ekaterina Moreva from Italy, and I hope that. Yeah, Ekaterina,
okay.
You are with us?
Yes. Yes, but please turn off the microphone because I see echo. Okay, now it's okay. So first of all, I would like to thank. Hello. Can you hear me? Confirm. Can you see my presentation?
Пошлите, пожалуйста, кого-нибудь, чтобы меня управление дали. Ага. Хорошо, спасибо. До свидания.
Can you hear me? Вы слышите? Подтвердите просто.
Катя, мы слышим, продолжайте.
Все, хорошо, просто какие-то помехи были. So, first of all, I would like to thank organizers for the invitation. Unfortunately, I can participate only in this forum. And today I'm going to talk about the problem of biosensing and also our last results, where we measure the temperature of neurons during the different neuronal activity. So this work has been done in a quantum optics group headed by Marco Genovese in Istituto Nazionale di Ricerca Meteorologica, in collaboration with Department of Drug Science and Technology, headed by Valentina Karabeli, and Institute of Organic Chemistry and Biochemistry of Czech Republic. This is outline of my presentation, and I would like to start from a brief description of the physics of NV centers, the basic electronic and spin properties, the concept of quantum sensing with NV centers, with focus on bioapplications, and then show our last results, where we, for the first time, measure the temperature variation associated to different patterns of neuronal activity. So, diamond has properties which make it unique for a very large range of applications, because it's very hard and optically transparent material, biocompatible and chemically inert. In experiments with biosensing, it's usually used in form of a bulk crystal, nanodiamonds with different size from tens to hundreds nanometers, or different nanofabricated structures. The crystalline structure of diamond can include different impurities like nitrogen, silicon, nickel, and many others, and these impurities can be natural or artificially created. The most common and most studied defect is NV central, nitrogen NV central, which consists of substitutional nitrogen atom and neighboring vacancy. And this central in diamond has a very stable photoluminescence in red range when we pump this defect by green laser. The single defect inside the crystalline structure can be considered as an atom-like system with a single photon emission, and it can be useful for quantum information or metrology, for example, as a single photon source. Small bright nanodiamonds with stable photoluminescence can be used in biology and medicine as a markers, while unique properties of electron structure of NV center allows to use it as a nanoscale sensor for the measurement of the temperature or electromagnetic field. And it's important that these sensing capabilities are maintained under the room temperature conditions. So the electronic energy level structure of NV center presents a ground state, excite state, and two metastable states. The ground state is a triplet which splits by spin-spin interaction on the singlet with spin 0 and doublet with spin ±1, separated on the zero field splitting frequency, which is about 2.87 gigahertz. And this frequency depends on the temperature because, for example, with heating, the spin-spin interaction changes and also this frequency changes. Once optically excite, depending on the initial spin state, different decays paths are possible. For example, if we in the state with spin 0, when spin conserving and radiative decay occurs, and we can observe a large photoluminescence. If the initial spin plus minus 1, when two paths are possible. The first one again for the same radiative transition, and the second one for the non-spin conserving, non-radiative transition, where the system and the end goes to the state with spin 0. That's why this state is more bright respect to the state with spin plus minus 1. And we called also like a bright and dark states correspondingly. If we illuminate our system in continuous way, we can initialize our system in this state with spin 0, while different intensities of spins allows us the optical readout. And the technique which used for it is optical detected magnetic resonance, which combine optical measurements with electron spin resonance spectroscopy. So the technique is quite simple. Let's imagine that we have a sample with NV centers and pump by green laser, collect the green red fluorescence from the sample, and at the same time, we also apply a driving microwave field and start to scan it near a certain range. At some moment, we can observe a dip in the fluorescence, which corresponds to a resonant transition between two states, plus minus 1 and 0. And without any external magnetic field, these two states are degenerated, and if we apply external magnetic field due to the Zeeman effect, these dips splits, and the distance between these dips is proportional to the projection of external magnetic field. It allows, for example, in bulk crystal with ensemble of NV centers, reconstruct the magnitude and also the orientation of a magnetic field, so to make a magnetometry. With the same method, we can measure also the temperature, because as I said before, the zero field splitting frequency depends on the temperature. And over the normal temperatures, it has a linear dependence, and sensitivity of this method depends how exact we can estimate the drift of this dip, the shift. And of course, it depends on the contrast of the dip, the line width, and also the number of NV centers or the number of collected intensity. These unique properties and also biocompatibility very interesting from point of view of biosensing. And in the last years, different works have been done. For example, in magnetometry, it's the famous work when was measured the neuron action potential from a marine worm. So it's a macro object, but was measured the action potential. Or in another work, the magnetometry of iron nanoparticles were made in tissue. Another line of research is thermometry, and the pioneer work here is work of Lukin, where we measured the gradient temperature inside the living cell, and the heating was also produced by nanoparticles inside the cell. In these two works was considered a thermogenic response inside the nematode worm with nanodiamonds inside. So, but in all these works, it was not the real biological signal. It was just a heating introduced by experimenter or, for example, some stimulation, but not the real biological effect. That's why in our work, we wanted to investigate the real biological phenomenon, it's a spontaneous firing activity of neuronal cells, and see what happens on the single cell level if we stimulate, for example, the firing activity, and then in some mode to block it. And in our experiments, we use two different chemical substances. The first one is a picrotoxin, which blocks inhibitory synapse and cellular activity increase due to the constant opening of the ion channel. So the, more or less in 2 times the activity becomes higher. And the second substance which totally block the neuronal activity, even the basal one. As a sample, we use mouse hippocampal neuron incubated in vitro for 10 days. And as a sensor, nanodiamonds with a size about 200 nanometers with very low concentration. And the first step was to understand what time is necessary for the nanodiamond internalization. And on this slide, you can see a micrograph of a cell with nanodiamonds inside. And this is after the 5 hours of incubation. So its time is enough for the penetration nanodiamonds inside the cell and prepare the measurements. The second step was to estimate the parameters of the measurements, because all measurements with biological samples required very accurate selection of the parameters, like laser power, the microwave power, nanodiamond concentration, because all of it can change the neuronal activity, or, for example, the form of the signal. We prepared a set of tests and defined the best parameters as a threshold between the sensitivity and the viability of cells. Because, of course, we can apply a high potential laser, but in this case, our cells will die. So, all measurements of electrical activity of cells were performed by a commercial platform, MEA system. It's a multi-electrode array with 60 electrodes, which allow the parallel data acquisition. And from this data, we can estimate the medium frequency, the form of the pulses, and so on. And the temperature measurements were performed in inverted optical microscope. It's homemade, with integrated part of a single photon-sensitive imaging and ODMR part. The sample was placed in a temperature chamber with microwave antenna and also with external control of the temperature. So the protocol of the measurements is quite simple, because we don't have enough time for the measurements, so all measurements must be very short. And the first step was a cell selection, so to find the cell with nanodiamond inside. When we prepared, when we measured ODMR spectrum for 1 minute, and also the differential ODMR spectrum, it's some kind of a static lock-in. In this range, linear range, we estimate the slope and fix the microwave frequency near the zero, and measure the number of counts for 1 minute. After that, our cells were stimulated, and we repeat the measurements of the counts for another minute. And the difference in counts is related with temperature variation, so by through this formula. So for us, it's enough to measure the difference in the counts.
Ekaterina, you have only 1 or 2 minutes maximum.
Yes, because it's quite difficult. So nanodiamond inside,
you have a lot of material,
not stable.
So it is impossible to put in 20 minutes. It is a lot. So
Yes.
please maybe skip something.
Yes, but it's okay. Let's the last slides. So for understanding what happens at different neuronal activity, we prepared two types of the test. The first, it's a control test. It's a set of tests which allows us to exclude different artificial change of the temperature, for example, due to the heating or due to the chemical reaction. When we applied the stimulation to our system and measure the temperature before and after the picrotoxin solution. And for 10 different cells, we observe the temperature variation in 1 degree respect to the control one. To be sure that this heating relate in some way with neuronal activity, we decided to totally block the neuronal activity. And in this case, we observed the decreasing of the temperature on the 0.5 degree. So we totally block neuronal network has less temperature than with basal firing activity. And it's for the first time we measure temperature variation associated with the real physiological phenomenon on the cellular scale. Of course, at this moment, we cannot say exactly, or it's only the firing activity of cells, or maybe also there are different metabolic processes inside. And that's why our future steps, future plans, is to improve the sensitivity of our method. And for example, with better quality of nanodiamonds, with tracking of nanodiamonds, to use also functionalization of nanodiamonds, which allows us to go in the specific subcellular areas like the mitochondria and measure near the mitochondria and maybe make some gradient map, and also to prepare synchronized measurements when we plan to integrate with electric measurements with optical one. So it allows us, and it will allow us to use electrical measurement as a, for example, trigger for our measurements. And as a summary, so first of all, we have found the biocompatible conditions for our experiments in intracellular temperature measurements. And we demonstrate that 5 hours is enough for the nanodiamond internalization. And for the first time, we detect the temperature variation on the single cell level associated with different neuronal activity of the network. And thank you for your attention. Here there are different papers, and these results you can find in Advanced Science paper. It's an open access journal paper, and also some reviews, our reviews and methods how to improve sensitivity during the biosensing. So thank you for your attention.
Okay, thank you, Ekaterina. Now maybe 1, 2 questions. First questions from Alexei. Are you with us, Ekaterina?
Yes.
Are you with us? Yeah, okay.
Ekaterina, thank you for a very nice presentation. So I have several questions about first, about the one last slide. What's the duty cycle or frequency of the spiking of neurons? What about the activity on neurons, which gives us such a reasonable delta T? This one slide, yes.
Yes. Okay. So when we if we don't apply any stimulation, there is some basal activity, so a spontaneous firing of neurons.
Okay.
The size is about, so the duration of one pulse is about microseconds, but it's not only one, so it's continuous in time.
Okay,
so of course we measure some medium, some frequency.
Okay, good. And also I have a question about aggregation of nanodiamonds. Does it somehow not prevent, but is it difficult for cells? Maybe it will be some cause some toxic effect when they are aggregating.
Okay. Okay. We used very low concentration of nanodiamonds. It was 0.6 microgram when the threshold level is 250. So it's maybe 1 or 2 nanodiamonds inside the cell, but and not in each cell. So very low concentration. Of course, if you add a lot of nanodiamonds, also because we have electrons, so we start to yes, in some way to collapse inside. So it's very important to select the right concentration of nanodiamonds. And that's why we prepared a lot of different tests to be sure that we don't include some external parameters which can to act on our measurements.
Unfortunately, I need to interrupt you because our time is very limited. It is very, very nice to be, so it means that science has no borders now. New technology destroyed all borders and yeah.
Yeah, I hope.
It is really. Now we will be other speaker from the other side of our globe, другая сторона нашего глобуса, Светлана Лукишова.
Леша, добрый день. Вы меня не видите. К сожалению, камера почему-то не работает. Вчера она работала, но вы не увидите. Добрый день.
Мы тебя слышим, Света, это достаточно. Давай, показывай.
Ну, слава богу, слышите, я могу слайды перемещать. Слава богу. I'm Svetlana Lukishova. I cannot tell you from what university. I need to follow the rules of our state, New York. I will speak about liquid crystal in quantum optics and nanophotonics. If you try to find in Google quantum optics and liquid crystal, you will see quantum liquid crystal. This is for solid state physics and electrons. This is analogy to liquid crystal. I will speak about real liquid crystal. What is special about liquid crystals? So, I will speak only about thermotropic liquid crystal, the same liquid crystal used in display. About 1% of organic molecules melt from solid state physics to liquid state with liquid crystal phase before transforming into the isotropic liquid at higher temperature. The main building block of liquid crystal are rod-like molecules, disc molecules, even banana shape, or something like what this is popular liquid crystal with carbon rod shape. And liquid crystal has many phases. For instance, pneumatic, when rod-like molecules in one direction, smectic, that you have layers, and holysteric liquid crystal with chiral molecules, but here chiral molecules, they can self-assemble in space in a chiral structure and possible to prepare photonic band gap material from such liquid crystal, holysteric liquid crystal, and unique phase, the blue phase. You can see how in liquid crystal molecule can assemble in space in such complicated order. So what are special in physical properties of liquid crystal? A liquid crystal can align with especially rod-like molecule. There is technology for the alignment with less than 1 micrometer spatial resolution. I told you already self-assembly into photonic band gap structure, and you can see on my slide from liquid crystal, from powder, and from liquid crystal, you can see color photonic band gap structure. Very important high birefringes in very wide spectral range up to 0.3, even in not only in terahertz. High birefringes, even 0.5 its material. High thermal optical coefficient, high electro-optical properties, and very important, but liquid crystal order can be frozen in solid state, the so-called glassy liquid crystal made from polymer and oligomer. From this powder, possible to obtain the solid liquid crystal with aligned molecule. And a lot of defect and texture in a liquid crystal. Next slide. Here is outline of my talk. I will speak about a 4th generation of transparent optical component and patterning of liquid crystal. Next will be quantum nanophotonics, using liquid crystal in quantum nanophotonic. After that, I will describe our experiment on transit time of single photons through holysteric liquid crystal photonic band gap structure. Along the band gap, how transit time changes. And future prospect, very interesting area, topological defects in liquid crystal. I can present here only published results, and most of results published in this review paper, in this book, and in liquid crystal review, in a review paper using liquid crystal in optic quantum nanophotonics. So, what is 4th generation of transparent optics? The 1st generation are originally prism lenses, next gradient optics, refractive index gradient, and also uniform optics. Next generation display, electro-optics, changing of refractive index, changing birefringence. And 4th generation optics made of liquid crystal. This is micrometer thin film with spatially continuously varying orientation of anisotropic axis, and possible to make, and I will speak about very thin optic prism lenses. And this made possible due to modulation of geometrical phase, specifically puncturatum Berry phase. And moment. So, what is puncturatum Berry phase? When the polarization of wave undergo continuous sequence of transformation following the closed path in space, space of polarization state. For instance, Poincare sphere, the wave acquires the phase shift. And this phase shift determined only by geometry of the polarization pattern. And this geometrical phase shift, geometrical phase induce the overall front reshaping. This is the main idea. This phenomenon was known from 1950, even earlier, but in optics it was discovered, the most attention was paid when a liquid crystal became available, and most important, orientation of progress in liquid crystal alignment. This, it's like diffractive wave plate, they exhibit the high diffraction intensity efficiency of Bragg grating, but in very thin micron thick layer. So this is a low-cost technology, and in contrast, for instance, with metamaterial, who also can serve for this purpose, they have 100% efficiency in wide spectral range. So I would like to mention the main idea was introduced by Soviet, this time Russian scientists working in Florida, Boris Zeldovich and Nelson Tiberian. They even applied to patent to this. Unfortunately, I don't know why there is no on the screen the pattern. Yesterday I checked, but should be pattern of this alignment for spherical, for lens, and for prism. So what this is for prism, and unfortunately for spherical lens also alignment with 1 micrometer resolution. How looks these elements? You can see they can be scaled with a big diameter. On the 100 micrometer polymer with photo alignment and thickness of liquid crystal only 1 micrometer, and it's possible to make freestanding film. Next. Using liquid crystal, possible to switch this lens, and using with solid liquid crystal, possible to switch with optical, with laser, with liquid crystal, possible to switch with electric field. Very important for quantum optics, Q plate, how to make from the circular polarization of specific handedness, beam with orbital angular momentum of light, that's important for secure quantum communication. So, and using Pocket self, possible very fast switch polarization and different momentum to create. So patterning, how small patterning can be made with liquid crystal. In focus ion beam, possible to make the very small grooves for alignment of liquid crystal, but the best alignment, the best patterning is 0.9 micrometer. This is micrometer size patterning in liquid crystal. Next, quantum nanophotonics. So using liquid crystal, first of all, easy to dissolve, disperse different type of single emitter, including nanocrystal disperse, and I will speak about this our result. Possible to align of emitter with dipole moment for definitely linear polarization of single emitter fluorescence for secure quantum communication. Holysteric liquid crystal can self-assemble in one-dimensional photonic band gap for one polarization that follows the direction of liquid crystal molecule, band gap for polarization of opposite handedness. The wave does not see any band gap. This is a very important property. Glassy liquid crystal polymer can make frozening of into solid state, the orientation and orientation of dye molecule. and very important tunability of property in liquid crystal provides tunability of nanostructure. So here are the results, our results and results of our groups of aligning single molecule by nematic liquid crystal. So we have di-molecules and one polarization component is much brighter than in our polarization component. And here polarization, so-called degree of polarization, exactly what emitting the dipole perpendicular to alignment direction. And this is results with the so-called dot inroads of Chigrinov group, also alignment with liquid crystal. This is schematics of holysteric liquid crystal, photonic bandgap materials, and you can see that one circular polarization following rotation molecule of liquid crystal exhibits the reflects selective reflection, and in our polarization transmit like in isotropic state. And it's similar to multi-layer dielectric mirrors, similar the reflectivity is 0 and along the radius, similar reflectivity, but for only one polarization of definite handedness, and very important, the wavelength of selective reflection. And with relative narrow spectral band. Next. Okay, here are our results on definite polarization. This is image of a single molecule confocal microscopy image of colloidal nanocrystal quantum dots, single colloidal nanocrystal quantum dots. You can see blinking here, and the if maximum emission of these dots on the band edge of this is a profile of holysteric liquid crystal. In this case, you have circular polarization and enhancement of fluorescence of a quantum dot. This is because of density of state on the band edge higher. And we observe anti-bunching in such structure. And here the results with nanocrystal doped with rare earth, with 30 nanometer nanocrystals. And again, for polarization on the band edge, we observe definite circular polarization of definite handedness at the output of this structure. This is on the level, this is not single photon level, but this is a single molecule confocal fluorescence microscopy. Here are our results also with nanocrystal colloidal quantum dots in holysteric liquid crystal photonic bandgap material, glassy liquid crystal, solid state. You can see profile of transmission of such structure and intensity, fluorescence intensity with cavity, holysteric microcavity resonance from 16 nanometer, from 76 nanometer to 16 nanometer resonance, and enhancement, approximately 5 times enhancement of fluorescence in such photonic bandgap structure and fluorescence photon anti-bunching in this structure. Next transit time of single photon from holysteric liquid crystal photonic bandgap structure. But along this bandgap, both how transit time changes. We use Hong-Umandel interferometer with spontaneous parametric down conversion and indistinguishable single photons. This is a retroreflector and the so-called observe the so-called Hong-Umandel dip when this path is equal for these two photons. We put holesteric liquid crystal into one of the arm of interferometer, and measuring the shift of Hong-Mandel dip, we observe and we rotate holesteric liquid crystal. When we rotate holesteric liquid crystal, photonic band gap shifted, and we can measure along the whole band gap, along the whole edge of band gap. We can measure changing in time, femtosecond resolution, how the time transit time changes. Relative polarization that have that see only isotropic properties. So move so slowly. I don't know why this slide does not show. Okay, next. But you can see how this is a polarization that doesn't see band gap, and this polarization which rotates the crystal, and band gap can be moved and measurements only on one wavelength, length 727 nanometer. So this is unfortunately the results. I don't know why on this computer don't see, and this is main results. Here are the main results. So we use two different type of profile. One profile and another profile rotating the sample. And here is a transmission profile of one. This is band gap. And you can see we have 250, up to 250 delay of one circular polarization in our relative in our polarization, and how change this transit time.
Svetlana,
here you can see.
Svetlana, excuse me, time is the same in your side
Okay,
and our
okay,
side.
you can, yes, you can see advance and delay along the band gap, okay? And also very, I would like to draw your attention how to use this transmission profile of this liquid crystal, holesteric liquid crystal photonic band gap material. This is unique material, but reflective index changes monotonically. And there is the whole cycle of work on analogy of transmission of a particle through potential barrier. And there is theory that at some length there is no changes of transmission time. And several groups try to model using multi-layer dielectric mirror, but they failed to model because of trapping mode, surface mode, when refractive index sharp. And this holesteric liquid crystal with varying refractive index can help. And the last slide, future prospect. There is a very important direction of topological defects, very multiple defects, and you can see in my slide in background also some defects. And this is defects a consequence of broken symmetry in ordered system, and they are broken symmetry important for understanding many phenomena in physics. And defects in liquid crystal, a lot of paper investigated for studying different process. Even the evolution of early universe were also defects and broken symmetry. And the last slide, you can see what this is on background. This is blue phase in a polarizing microscope. And I would like to thank the students who worked with me, and a group of Robert Booth, my collaborator. Thank you. And question, please, if I have time.
Okay. Okay, thank you, Svetlana. It was impressive presentation. I think that maybe one question, not more, because we wait when our ship will start from Samara by Volga River. So it will be start in 3 p.m. our time. It is, I don't know, what is time now in your place?
In my place, 7 a.m.
Okay. So, could like to ask something, Svetlana Lukishova. Who ready? I think that now, as I told a couple minutes ago, that new technology gives us possibility to contact with you directly by using WhatsApp, Telegram, and so on. And in this case, I think that if you have some questions to Svetlana, welcome, please. So it will be
Okay, welcome. And this is really for quantum nanophotonic, this is very important material. And there are some pitfalls of using liquid crystal. Some liquid crystal has own fluorescence, but we overcame this fault. And you saw anti-bunching in liquid crystal.
No. Okay, thank you, Svetlana, again, and we will be in touch. Thank you. Я не вижу, где этот парень? Поверните. Тут очень сложная какая-то система.
Морева, Лукишова и... Я не понял.
Я не понял.
Они почему-то...
Нет, позвони.
Ну? 35-го?
Ну вот смотрите, значит, кто был, значит, вместо Морева, Светлана.
Прием. Вот Пастернак, вот же.
Okay, Пастернак, это ваш, okay. Okay, excuse me, we have the short presentation of Dr. Pasternak. I think it will be unfortunately, I forgot it. It is a very complicated schedule of this conference. It is not easy to find who is today, who is tomorrow. I don't know. So you have short time, 15 minutes maybe.
Okay.
Be carefully. Okay. Because you know that we have
maximum one hour. Yes.
Hard schedule.
Okay. Firstly, I want to say hi everybody, and it's nice time in here. It's a beautiful place and a beautiful building to have this presentation here. So yes, let's start. Let's proceed. Okay, today it's a big pleasure to present our big joint scientific work, which is named Low Temperature Single Photon Silicon Vacancy Luminescence in bottom-up grown nanodiamonds. So it's a joint scientific work. So our co-workers' emblems is displayed in the first slide here. So yes, let's proceed. With the outline of my speech, of my talk today. The first thing I want to put your attention in a subject of our study and the actuality of our study. Then we will then I will describe low temperature silicon vacancy photoluminescence in different nanodiamonds with different structures, with different sizes, and we will see how changes SIV properties of these diamonds at low temperature and their single photon sources, their single photon properties. And then we will have some conclusion of my talk and some future plans I will show you. Yes, the first thing that we are developing, we have been developing so-called bottom-up approach for the synthesis of nanodiamonds, and it is well-known, three well-known approaches, three well-known techniques: detonation synthesis of nanodiamonds, high-pressure, high-temperature method, and chemical vapor deposition method. So it is believed that this method give us opportunity to product, to synthesis nanoparticles with a better structure quality. So we are synthesized diamond from the atom to the nanostructures. That's why we choose these nanodiamonds. So here in the right part of my slide, you can see a carbon phase diagram with two main methods that we chose for our study. It's HPHT nanodiamonds with a high temperature and high pressure, and the chemical vapor deposition, so-called metastable phase of production nanodiamond. So in this case, we use methane as a gas as the source of sp3 hybridization of molecular, and here we have a diamantane as a diamond-like structure. Yes, actuality of our work is that color centers in nanodiamonds can be applicable in nanoelectronics, in biomedicine, metrology, and quantum technologies. So here is some of applicants of our work. You can find this application in some photonic crystals, which should be used for the bright and stable single photon sources, for the bright source of luminescence. So we have different theoretical works. How can small ensembles in nanodiamond interacts? Not nanodiamond, not in nanostructure can interact and gain each other, and we have a bright stable emission from this, and we also can use it in different planar waveguides here. Yes, here is the subject of our study. It's silicon vacancy centers. My colleague and friend Alexei mentioned some peculiarities of enhancing this luminescence with SIV centers. Ekaterina also working with another color center in diamond, nitrogen vacancy center. So in this work where we investigate silicon vacancy center. It's also atom-like structure. It has silicon atom in interstellar position between two vacancies in diamond crystal. So it has okay, God bless you. It has a strong zero phonon line in 738 nanometers. Approximately 70% of emission is concentrated in zero phonon line, and a weak phonon line has approximately 20 or 30%. So it has at the right picture you can see the energy destruction of SIV centers in cold temperature, so-called cryogenic temperature. It has ground state and excited state, which in low temperature and laser radiation, it has four transition. Next, we use SEM characterization method to describe our nanocrystals. So the first part we share between each other two types of CVD nanodiamonds, which is grown from detonation nanodiamond seed, and with our next method is spontaneous nucleation, where diamond originates presumably on defects on germanium substrate. So we can achieve nanodiamonds with the sizes approximately 50 nanometers. And the next point, we characterize their quality of crystal structure, and we found that spontaneous nanodiamonds had a better quality than seeding one nanodiamonds. The next point, we characterize our nanodiamonds at room temperature firstly, pre-characterization technique. So we found that it has noticeable diamond Raman peak, and SIV center peak. So the full width at the half maximum of this PL line is approximately 7-9 nanometers, which is broader than in a bulk diamond, and it indicates the presence of some of deformation inside crystals. Then we use low temperatures in order to work in order to understand the structure, low temperature structure of ensemble of our centers. So we have at the first line we have data for the seeding nanodiamonds, so-called seeding nanodiamonds, and the low one for the spontaneous nanodiamonds. And for this one, for the spontaneous nanodiamond, we found several transitions, which indicates us that we can work with the single transition with a resonant mode, with a resonant laser mode at a low temperature. The next, we try to comparison between spontaneous and seeding nanodiamonds. What happens with the width of these lines? So we found that for spontaneous nanodiamonds, it has 1 or 3 gigahertz in the width. So it's in 3 times broader than lifetime limited line width at 15 kelvins. Also, it has good polarization sensitivity, this single transition, and it demonstrates quite stable behavior. The next step of our study is try to work with our nano diamonds, because silicon substrate has a great adhesive properties, so we have no opportunity to manipulate with our diamonds, with our grown nano diamonds. And this part we try to switch from the silicon substrate to germanium substrate. And at this point, we have a controllable formation of SIV centers, and we also found that morphology of so-called germanium grown nanodiamonds particles is different from silicon one. And we found that in the silicon, in the germanium substrate, we have more polycrystalline structure than in a silicon substrate one. Nevertheless, we understand that we work with the big ensembles of centers, and the big question is, could we work with a single transition, and so-called to work with a single dipole in ensemble, from ensemble. So we have an experiment that we have with non-resonant excitation. We have a broad dispersion of silicon vacancy properties from in a range of 20 nanometers. So we have a broad types of silicon vacancy transition, which means that we have a big cluster of single transitions. But nevertheless, with the resonant excitation, we have ability to work with each of these transition. And we can see that that we have a big particle with a big ensemble of SIV centers, and also with a resonant excitation. It's a really complicated technique, but it works. We can find transition also in the silicon nanodiamonds and germanium nanodiamonds, and we can work. We have ability. We're able to work with this transition and work with this like a single transition. So we found that it also has a good polarization behavior, and we due to that we have a Brown twist interferometer in our confocal setup. We checked their autocorrelation, second order correlation function, and we found that the deep of this function meets up that we work with a single photon emission of one transition. So the final step, this is small addition for our work. We work with a second type of diamonds, is HPHT nanodiamonds, which synthesized from adamantane and tetrakis. It's So it is believed that HPHT nanodiamonds has a better structure quality, and we can find different nanodiamonds with different sizes from 1 micrometers to 100 nanometers. So due to the correlation spectroscopy, we analyze these particles, and we found that we have opportunity to controllable work with silicon vacancy centers. And the next point, we have a big comparison between CVD nanodiamonds and HPHT nanodiamonds. And we found that for HPHT nanodiamonds, we have a range in silicon vacancy luminescence, which is in the 5 times narrower than for CVD diamonds, and this is a marker of better structural quality of HPHT nanodiamonds. It should be more stable and more brighter than CVD1, but it has not so big spectral ability to address for single SIV center as a CVD nanodiamond. So this is a conclusion of my talk. The first one, we work with 5 nanometers sized spontaneous nucleation nanodiamonds, and we have to address up to 12 single SIV centers. The second one, we have an ability to transfer and manipulation with 300 nanometers CVD diamonds, and we also found that it will be possible to switch to another photonic structures, maybe to the future plans are to incorporate it in different photonic crystals and investigate their luminescence properties, lifetime kinetics, and so on. And the finish of our work is to finding that we have spectral access to each of SIV center in individual CVD and HPHT nanodiamonds, big nanodiamonds, and due to the non-resonant laser mode. And the localization of their lines lies in a shorter range, which have several nanometers, yes, which indicates for HPHT diamonds higher structural quality than CVD1. At this time, I want to finish my talk, and thank you for your attention.
Okay. I'm very glad that you was absolutely in time, so it is very nice. So we have 1 or 2 questions, maximum, minimum, 2, because time is very short, and then the people will use taxi to catch the boat, but I'm not sure that it's possible.
Okay.
Who will ask? No.
Okay, thank you.
I think that it is very nice for you, yes. My congratulations, it was interest. Okay, so section is finished, and can prepare for trip.
Больше так, а что говоришь, вот монитор с полным валяется, что там? У нас они как, вас просто лежат без дела, что ли, ничего? Ну, как бы нужны, но... Ну, в смысле, они подвышены, рабочие стоят. Как с Кашовой? Все удалось? Все удалось. Так, я двинул...